In the vast silence of the cosmos, there exists a galaxy unlike any other, a frozen relic from the dawn of time known as NGC 1277. While most galaxies dance through cosmic time, colliding and evolving in spectacular fashion, NGC 1277 remains eerily untouched, like a museum piece suspended in the dark. But what truly sets it apart isn't just its ancient stars or stillness, it's the monstrous black hole at its core, one of the most overgrown ever discovered, devouring light and matter with an appetite that challenges everything we thought we knew about galaxy formation. This is not just a galaxy, it is a cosmic fossil powered by a force so extreme, it threatens to rewrite the rules of the universe. But before we continue, subscribe to the channel so you don't miss out on any of these videos. NGC 1277 sits like a ghost in the Perseus cluster, roughly 220 million light-years away from Earth. At first glance, it looks like an ordinary lenticular galaxy, smooth, featureless, and seemingly quiet. But as astronomers began to peer deeper into its heart, they found something so staggering that it shook the astronomical community to its core. An ultramassive black hole, 10 times more massive than it should be. This black hole isn't just oversized, it's obscenely overpowered, accounting for a jaw-dropping percentage of the galaxy's total mass. While most galaxies reserve only a fraction of a percent of their mass for their central black holes, NGC 1277's black hole contains nearly 14% of the galaxy's total stellar mass. That's not just unusual. That's cosmic tyranny. To understand how bizarre this is, you need to appreciate the balance that exists in most galaxies. The Milky Way, for example, has a black hole at its center called Sagittarius A, which weighs in at about 4 million solar masses. It's substantial, but when compared to the galaxy's total mass of around 1 trillion solar masses, it's just a drop in the cosmic bucket. NGC 1277, however, flips this paradigm on its head. Imagine if the Sun was orbited not by Earth, but by a collapsed star so powerful that it dictated every orbit in the solar system. That's the scale we're talking about. This galaxy doesn't just contain a black hole, it orbits one. But NGC 1277's story is even stranger. For reasons still under investigation, it seems to have stopped forming stars billions of years ago. Most galaxies grow by merging with others and by pulling in gas and dust to spark star formation. But this one? It's done. It's finished. It lives in a kind of cosmic retirement, having formed the majority of its stars when the universe was less than 4 billion years old. Since then, it has barely changed, making it what astronomers call a relic galaxy. It's like finding a fossilized dinosaur with living skin still intact, frozen in time, a pristine sample of what galaxies might have looked like in the early universe. The sheer size and power of the black hole inside NGC 1277 has baffled scientists. Some believe it formed unusually early, gobbling up everything around it in the chaos of the young universe, and then somehow, NGC 1277 was locked in stasis, immune to the typical galactic cannibalism that causes galaxies to evolve. Or perhaps it did consume others, silently devouring small galaxies that drifted too close, growing fatter and darker with every meal. In either case, this galaxy doesn't just break the mold. It pulverizes it. As astronomers used powerful telescopes, Hubble, Gemini North, and others, to map the velocity of stars spinning around the center of NGC 1277, they noticed that these stars were racing. They weren't calmly orbiting the way stars do in other galaxies. They were being whipped around by the gravitational might of an invisible force, a force so compact, so dense, it could only be one thing: a supermassive black hole with a mass of more than 17 billion suns. That's not just unusual. That's mythic. And yet, it doesn't stop there. Because NGC 1277 might not be alone. It may be just the first of many relic galaxies hiding in the shadows of the universe, ancient beasts from a forgotten era when black holes ruled with unchecked ferocity. It's as if NGC 1277 is a survivor from a cosmic apocalypse we never saw, a remnant of the universe's wild youth, preserved like a museum exhibit, warning us of an epoch where the rules were very different. But what truly elevates the story of NGC 1277 from the realm of the strange to the level of the profound is what it tells us about time. Galaxies evolve. They change, stretch, spin, collide, and morph into entirely new shapes. But NGC 1277 is none of that. It's the what if, in a universe full of inevitabilities. What if a galaxy didn't change? What if it formed in a blaze of violence, and then simply stopped? This galaxy is a contradiction, ancient and yet powerful, small in scale and yet housing one of the most massive black holes ever found. The fact that it hasn't changed in over 10 billion years tells us something critical about the history of the universe. It tells us that there was a time, early on, when conditions could create galaxies that were dominated by their black holes instead of the other way around. And it opens the door to a chilling question: what if there are other galaxies out there, equally ancient, equally strange, and equally hungry? NGC 1277 is not just a scientific curiosity, it's a philosophical one. It forces us to rethink the role of black holes in galactic formation. Did black holes come after galaxies, as most models suggest? Or did they come first, forming the seeds around which the earliest galaxies coagulated? If the latter is true, then galaxies like NGC 1277 are not anomalies. They're the original blueprint. They are the forgotten kings of an ancient regime. The answers to these questions could redefine how we understand the very architecture of the cosmos. We might be standing on the edge of a discovery that rewrites the timeline of galactic evolution, where the oldest galaxies are not the smallest, but the darkest, the densest, and the most dangerous. And the mystery deepens when we ask, why did NGC 1277 stop evolving? Why did it halt its star formation so early, while others continued to change and merge and shine? What environmental or internal condition froze it in place, like an insect in amber? One theory is that it lost its gas supply early, perhaps stripped away by interactions with nearby galaxies, or consumed entirely by the central black hole. Without gas, there can be no new stars, and without new stars, the galaxy becomes a tomb, a celestial mausoleum orbiting a devouring singularity. NGC 1277 is the ultimate cosmic paradox. It is small, yet contains one of the biggest black holes in the universe. It is ancient yet more powerful than many of its peers. It is dead, in the sense that no new stars are born there, but at its heart beats the most violent force in the known cosmos. It's like a vampire galaxy, no longer alive in the traditional sense, but still moving, still feeding, still dangerous. In a way, this galaxy may be more honest than our own. The Milky Way wears the mask of life, with its sparkling arms and bustling neighborhoods of star formation. But at its center is a killer, a black hole waiting patiently, slowly consuming whatever drifts too close. NGC 1277 strips away that illusion. It is the naked truth of what galaxies may become, the flesh stripped away, the energy spent, leaving only the monstrous heart pulsing at the core. This raises yet another terrifying possibility. If NGC 1277 is what happens when a galaxy completes its life cycle, what if we are on the same path? What if the Milky Way, too, will one day become a fossil galaxy, its stars grown old, its gas depleted, its central black hole having fed to contentment? Is this our future? Is NGC 1277 not just a relic of the past, but a mirror held up to the fate of all galaxies? The journey to understanding NGC 1277 is not over. New telescopes, like the James Webb Space Telescope and the upcoming Extremely Large Telescope, will soon give us sharper views of galaxies like it. We may discover that NGC 1277 is not unique. We may find others, hundreds, perhaps thousands, lurking in the darkness, remnants of a forgotten epoch when the universe was younger, wilder, and ruled by monsters. As we dive deeper into the enigma of NGC 1277, the galaxy continues to reveal clues, not just about itself, but about the infancy of the universe. To see NGC 1277 is to peer into a frozen record of galactic evolution halted in its tracks. It is a cosmic fossil, untouched by the turbulent galactic mergers and dynamic star formation that characterize so many of its modern cousins. Instead, it exists as an island of calm around a tempestuous core, where the gravitational monster at its heart continues to shape the very identity of this galactic relic. The immense black hole within NGC 1277, estimated at more than 17 billion solar masses, is one of the most overmassive black holes ever discovered. For context, this makes it several times more massive than the black hole at the center of the Milky Way, and significantly more massive than what astronomers would expect for a galaxy of its size. Usually, there's a well-established relationship, known as the black hole bulge mass relation, where the mass of a central black hole is roughly proportional to the stellar mass of the galaxy's bulge. But NGC 1277 flouts this law spectacularly. In fact, the black hole within NGC 1277 is so massive that it accounts for an estimated 14% of the galaxy's total stellar mass. This breaks conventional understanding. In most galaxies, including those in the early universe, supermassive black holes account for roughly 0.1% to 0.5% of their host galaxy's bulge mass. That means NGC 1277's black hole is more than 30 times more massive than expected. Such a deviation isn't just a statistical outlier, it's a glaring exception, a fundamental challenge to current astrophysical models. But why does this matter? Because this anomaly suggests that our understanding of the relationship between black holes and their host galaxies may be incomplete, or worse, fundamentally flawed. Are galaxies born around black holes, or do black holes grow within galaxies as a consequence of galactic evolution? In the case of NGC 1277, the evidence seems to point to the former. It suggests a universe where some black holes were so voracious, so efficient in their consumption, that they could outpace the very galaxies that gave birth to them. And NGC 1277's location in the Perseus cluster adds another layer of intrigue. The Perseus cluster is a bustling neighborhood of galaxies, known for its massive central galaxy, NGC 1275, and for housing one of the largest known galaxy clusters in the nearby universe. In such a busy region of space, galaxies often interact, collide, and merge. Tidal forces stretch them, and gas-rich encounters fuel starbursts. But NGC 1277 remains eerily untouched, as though it slipped through the cosmic chaos without ever engaging in these galactic brawls. That untouched quality gives astronomers a priceless opportunity. By studying NGC 1277, they can look back in time, not metaphorically, but literally. The light reaching us from NGC 1277 left over 220 million years ago, and the galaxy itself hasn't significantly changed in over 10 billion years. It's a time capsule, allowing researchers to reconstruct what galaxies looked like shortly after the Big Bang, when the universe was in its turbulent infancy. But just how did this galaxy form? The prevailing hypothesis is that NGC 1277 was once a part of the universe's first wave of massive galaxy formation. Around 10 to 12 billion years ago, the universe was a furnace of chaotic energy, with matter coalescing into proto-galaxies and black holes feeding at unprecedented rates. During this period, a small population of galaxies formed very quickly, generating most of their stars in a brief, intense starburst, then rapidly exhausting their available gas supply. In NGC 1277's case, it seems the galaxy underwent this exact evolutionary arc. It formed nearly all of its stars within the first billion years of its life, and then abruptly shut off. Perhaps it lost its gas to the hot intracluster medium of the Perseus cluster. Or perhaps its black hole grew so quickly and became so powerful that its energy output blew away the remaining gas, an event known as quasar feedback. This would have heated or ejected the gas necessary for star formation, turning the galaxy into a stellar graveyard. If this hypothesis is correct, then the black hole in NGC 1277 didn't just grow in tandem with the galaxy, it dominated it. The galaxy's fate was sealed by its own center, a dramatic reversal of the traditional view in which galaxies shape the evolution of their central black holes. This paints a darker, more deterministic vision of galactic history, one where the singularity at the center isn't just a product of the galaxy, it's the architect of its doom. Even more fascinating is the possibility that there are more galaxies like NGC 1277 lurking in the cosmic dark. Since their signatures are subtle, no grand spiral arms, no radiant bursts of new stars. They may be overlooked in traditional surveys that focus on star-forming galaxies or those with dramatic morphological features. But as telescopes become more advanced and surveys more precise, astronomers are beginning to identify a class of compact, old, high-velocity dispersion galaxies. These galaxies are small but dense, with tightly packed stars moving at incredible speeds. And at the heart of many of them may lie black holes as monstrous as the one in NGC 1277. These galaxies, collectively referred to as red nuggets, are thought to be the relics of early universe galaxies that never grew further. In the early cosmos, these red nuggets were common. But over billions of years, many were subsumed into larger galaxies through mergers. NGC 1277, however, survived. Somehow, it remained intact. It stayed compact. It didn't merge. It didn't grow. It remained preserved, a pristine specimen of ancient cosmic architecture. And that preservation opens up another realm of inquiry. What happens inside a galaxy that never changes? In a typical galaxy, stars are born and die, gas flows and compresses, and structures such as arms and bars develop over time. But NGC 1277 doesn't do any of that. Its stars are old, ancient, in fact, with ages pushing back over 10 billion years. These stars have been orbiting its black hole in predictable, unchanged paths for longer than the Earth has existed. That means NGC 1277 offers a glimpse into a unique type of cosmic equilibrium. The black hole governs everything, and the stars respond accordingly. It's a gravitational ballet choreographed by an ancient singularity. The entire galaxy functions like a massive, stable orbiting system, with little to no internal chaos. No new stars are disrupting the system. No gas clouds are changing the dynamics. No tidal interactions are stretching or warping the structure. Just pure, ancient gravitational order. But there's also something haunting about such perfection. Because it is static. It is sterile. It is unchanging. In the grand theater of cosmic evolution, NGC 1277 is a closed curtain. Its stars may still shine, but they are fossils orbiting a corpse. And yet, even in death, there is majesty. The monstrous black hole at the center may still accrete stray matter, perhaps the occasional star, asteroid, or gas cloud. As these objects spiral inward, they would be torn apart, heated to incandescence, and radiate energy in X-rays and gamma rays. These rare feeding events are the only signs of life left in NGC 1277, a flicker of violence in a frozen frame. Looking further into the future, the existence of NGC 1277 poses deep theoretical questions about galactic destiny. Is it possible that over cosmic timescales, many galaxies might evolve into similar relics? Will galactic mergers cease as the universe expands, leaving countless galaxies to exhaust their gas and become sterile? Will black holes continue to grow until they dominate not just galaxies, but entire galactic clusters? In this way, NGC 1277 is not merely a relic, it is a prophecy. A vision of what could become of many galaxies, including our own, as the universe ages and entropy takes hold. A galaxy where the lights go out, the stars fade away, and the only thing left is the dark, ever-hungry heart. As astronomers continue to study NGC 1277 with ever more advanced instruments, they hope to unlock further secrets about the early universe. Spectroscopic analyses, velocity dispersion measurements, and high-resolution imaging are all tools in the arsenal. But perhaps the greatest tool of all is imagination, the ability to look at this quiet galaxy and hear the echoes of a violent past. Because NGC 1277 is a whisper from the universe's childhood. It is the fossilized growl of a black hole that once roared, now buried in a galaxy that stands still while the cosmos moves on. What makes NGC 1277 so hauntingly beautiful is not just its defiance of galactic norms, or its monstrous central black hole. It's the fact that it holds still in a universe of motion. In a cosmos driven by entropy, by transformation, by relentless forward momentum, NGC 1277 is a moment of silence. It's the photograph of a firework mid-burst, a galaxy that raced through its evolution so quickly and so violently that it burned itself out before the universe could catch up. And now, all we're left with is the aftermath. The question we must keep asking then is, why? Why did NGC 1277 evolve in such isolation? Why did it not interact with other galaxies in the densely packed Perseus cluster? Why did it not grow larger through mergers, like so many of its early counterparts? These are not just idle questions. They are fundamental to understanding how galaxies become what they are. One theory that astronomers have considered involves NGC 1277's path through space and time. Some simulations suggest that it may have once dwelled on the outskirts of the cluster, where interactions are less frequent, and was only recently drawn inward by the gravitational pull of the cluster's core. If that's true, it might explain how it remained untouched, left to age in solitude before being enveloped by its modern surroundings. But the real enigma continues to revolve around the black hole. How did it grow so massive, so quickly, and why did it outpace the stellar population of the galaxy itself? Some researchers believe NGC 1277 could represent an ancient mode of black hole growth, one that was more efficient, more voracious, and more dominant than the modes we see in more typical galaxies. During the universe's first billion years, matter was denser, and gas was more plentiful. It's possible that the black hole in NGC 1277 fed on this bounty so aggressively that it grew exponentially, unchecked by the balancing forces that regulate black hole growth in other galaxies today. This also raises questions about the nature of feedback mechanisms. In typical galaxy evolution, black holes help regulate their own growth through feedback, expelling energy and material that limits further infall. But in the case of NGC 1277, that feedback might have been catastrophic. Rather than achieving a balanced stasis, the black hole may have produced so much energy that it sterilized its own environment. The galaxy, once teeming with star-forming gas, became a vacuum, devoid of the raw material needed to build more stars. It's as though the black hole won an evolutionary arms race, and in doing so, condemned the galaxy to a permanent stasis. That level of self-destruction is unprecedented. And it prompts a haunting metaphor. NGC 1277 is a cosmic Ouroboros, a serpent devouring its own tail. A galaxy whose central engine was so successful that it choked off every possibility for future change. And while that image is grim, it is also powerful. Because in the face of cosmic life cycles that stretch across billions of years, this is a reminder of the fragile balance that keeps galaxies alive. And yet, despite all this, NGC 1277 still glows. Its stars, ancient though they are, still shine. Their light still traverses millions of light years to reach our telescopes. And in that light is encoded the story of its formation, its struggle, its silence. Astronomers analyze this light, splitting it into spectra, measuring its redshift, decoding the elemental abundances, and in doing so, they reconstruct the life history of this ancient being. It tells a story of high metallicity, indicating that its stars formed from gas that had already been processed through earlier generations of stars. This suggests that star formation was rapid and intense. There was no slow buildup. The galaxy went through a sudden burst of star birth, forming a compact, dense population in a very short time frame. Then, suddenly it stopped. Just as quickly as it ignited, it extinguished. The reasons for that quenching remain speculative, but the leading candidate remains the overactive black hole. Its energy output was likely enough to heat or expel the surrounding gas, permanently halting star formation. In the grander scheme of astrophysics, NGC 1277 provides a unique laboratory for testing theories of galaxy evolution, black hole growth, and feedback mechanisms. It is a proving ground for computational models, offering a challenge to simulations that must now account for such anomalous relics. Cosmological simulations like Illustris, Eagle, and TNG-50 have made incredible strides in modeling galaxy formation across cosmic time. But NGC 1277 stands as a stark test case. If a simulation can accurately reproduce a galaxy like NGC 1277, its mass, its compactness, its velocity dispersion, and its black hole mass, then we may be closer to understanding the full diversity of galactic evolution. Furthermore, studying this relic galaxy also deepens our appreciation for just how rare and fragile galactic conditions can be. For every NGC 1277, there are thousands of galaxies that did not follow this path. They merged, they grew, they transformed. Many have bar structures, spiral arms, tidal tails, all signs of dynamic interaction. NGC 1277, on the other hand, is devoid of such features. It's a pure elliptical, devoid of dust, devoid of gas, devoid of youth. It is a cosmic elder, and it stands alone. But its loneliness also makes it loud. By existing outside the norm, NGC 1277 demands attention. It demands that we revise our models, that we ask harder questions. It reminds us that the universe is not always governed by neat, linear trends. There are exceptions. There are extremes. And these outliers are often the ones that teach us the most. They are the cracks in the model where the light gets in. Looking to the future, new instruments and observatories promise to peel back even more layers of mystery. The James Webb Space Telescope, with its unprecedented infrared sensitivity, will allow astronomers to peer deeper into the stellar populations of relic galaxies like NGC 1277. Webb can detect the faint, redshifted light from ancient stars and measure their compositions with greater accuracy than ever before. This will help determine exactly when the stars in NGC 1277 formed and how quickly they reached their current state. Meanwhile, the Vera C. Rubin Observatory will conduct massive surveys of the sky, potentially identifying more NGC 1277-like galaxies. The more relics we find, the better we can understand whether NGC 1277 is truly unique or part of a hidden population that has eluded detection due to its unassuming appearance. If more such galaxies are found, it will rewrite the narrative of early galaxy formation. It will suggest that the early universe was not just a place of growth and expansion, but also of rapid burnout and stillness. But beyond the science, there is also something deeply poetic about NGC 1277. It is a reminder that in a universe of light, there are shadows. In a cosmos of birth, there is also dormancy. In a sea of noise, there are silences that say more than the loudest explosions. This galaxy, though silent, speaks volumes. It speaks to the sheer diversity of the cosmos. It speaks to the violence of its past and the peace of its present. It speaks to the possibility that not all stories need to be long to be meaningful. For even in its stillness, NGC 1277 is not done teaching us. It is not done shaping our understanding. It is not done reminding us that the universe is more complex, more mysterious, and more awe-inspiring than we can ever imagine. And so we continue our journey into the heart of NGC 1277, this ancient, enigmatic relic of the cosmos, a galaxy that seems to have halted its evolution billions of years ago, and yet refuses to fade quietly into obscurity. The more closely astronomers examine this celestial fossil, the more it challenges the assumptions of galactic growth and evolution that have long been held in astrophysics. It is not merely a curiosity, it is a paradigm disruptor, a case study that forces us to look beyond statistical norms and face the sometimes chaotic, unpredictable nature of the universe. The measurements of its velocity dispersion, how fast stars move within it, reveal staggering numbers. These stars, tightly packed into a dense, spheroid structure, zip around at speeds that boggle the mind. Such speeds suggest that the gravitational well they are orbiting is not just deep, but unimaginably vast. This ties directly to the galaxy's central feature, its black hole. Estimates put the mass of this black hole at over 17 billion solar masses, which, when compared to the galaxy's relatively small size, places it vastly out of proportion. By contrast, the Milky Way's supermassive black hole is just over 4 million solar masses. In NGC 1277, the black hole constitutes about 14% of the total mass of the galaxy's stars, a ratio nearly unheard of. Most galaxies have black holes that are around 0.1% of their stellar mass. This black hole did not form overnight. It likely originated from a seed black hole in the early universe, formed from the remnants of massive primordial stars or through direct collapse mechanisms where dense clouds of gas collapse straight into black holes without forming stars first. But what makes NGC 1277's black hole truly monstrous is not just its size, but how quickly it must have grown. The conditions in the early universe may have allowed for an accelerated feeding frenzy, where the black hole consumed vast quantities of gas before the galaxy even had a chance to form more stars. This feeding phase would have been intense, unleashing winds and jets of energy that could have sterilized the surrounding medium, halting star formation entirely. And this takes us to the heart of the mystery: feedback. In astrophysics, feedback is the process through which black holes and stars influence the evolution of their host galaxies. Radiation, winds, and jets can push gas out of the galaxy, heat it up so it can't collapse into new stars, or trigger bursts of star formation. In most galaxies, feedback is a balancing act. In NGC 1277, however, the feedback seems to have been overwhelmingly negative, an almost surgical sterilization that stopped star formation dead in its tracks. That kind of precision destruction is rare, and it may mean that the black hole in NGC 1277 was among the most aggressive entities in the early cosmos. The environment of NGC 1277 also adds complexity. It lies within the Perseus cluster, a massive conglomeration of galaxies that interact, collide, and exchange matter in chaotic dances that span billions of years. Yet, NGC 1277 appears to have remained aloof from these galactic dramas. This raises questions about its orbital history. Perhaps it was once a lone wanderer on the edge of the cluster, skimming the outskirts where interactions were sparse. Only in recent epochs did it fall inward, settling among its more interactive brethren after a long solitary journey. This isolation could explain why it looks so untouched, like a cosmic museum piece, preserved in its original state, while all around it evolved and transformed. But even the Perseus cluster's environment could not preserve NGC 1277 without changes. Some recent observations suggest that while it shows little sign of external interactions like tidal stripping or mergers, there may be subtle hints of gravitational influences. Perhaps faint stellar streams exist in its periphery, too dim to be seen with current instruments, suggesting an encounter with a smaller galaxy that was absorbed without fundamentally altering its structure. These ghosts of past interactions may lie hidden in the faint outer halos, waiting for future telescopes to reveal them. Speaking of the future, the instruments that will help unlock NGC 1277's secrets are either already operational or soon to be launched. The European Space Agency's Euclid mission will map billions of galaxies, including their dark matter profiles, which will help astronomers understand how galaxies like NGC 1277 sit within the larger cosmic web. If NGC 1277's dark matter halo is unusually compact or massive, it may offer clues about how its early growth was regulated. Similarly, the 30-meter telescope and the extremely large telescope, giants under construction in Chile and Hawaii, will allow astronomers to resolve individual star clusters within NGC 1277 and determine their ages with unprecedented precision. This matters because if all of NGC 1277 stars are genuinely as old as they seem, formed within a tight window around 10 to 12 billion years ago, it would confirm its status as a relic galaxy, untouched by major events since the dawn of time. But if we find a younger population of stars hidden within, the narrative could shift. Perhaps it did experience minor mergers, or maybe a trickle of gas occasionally found its way in and sparked brief, localized star formation. The absence of gas and dust today doesn't mean it was always that way. Moreover, its compactness is not just an aesthetic trait, it's a fingerprint of its origin. NGC 1277 is far smaller than modern ellipticals of comparable mass, which are often puffed up by mergers and tidal interactions. This compact form tells us that the galaxy has not grown significantly since its formation. If anything, it has resisted change, holding tightly to its original configuration. It is a reminder that the early universe was a place of extremes, where galaxies could form quickly and violently, but where a lucky few managed to avoid the chaos of continued evolution. This lends NGC 1277 another nickname among astronomers, a red nugget. These galaxies, common in the early universe, are compact, massive, and red, indicating old stellar populations. Most red nuggets have since grown through mergers into the giant elliptical galaxies we see today. NGC 1277 is the rare survivor. It is a fossil record of what galaxies looked like in their youth, preserved in the cosmic amber of isolation. And that makes it all the more valuable. Because fossils are rare. And this one isn't buried, it's gleaming brightly in the heart of a galactic metropolis. By studying NGC 1277, we can rewind the universe. We can peer into an epoch when galaxies were just beginning to assert themselves, when stars were forming at breakneck speed, and when black holes had not yet settled into the quiet, regulated roles they play in most galaxies today. But perhaps the most unsettling question that NGC 1277 raises is not about how it formed, but whether its fate could have been ours. What if the Milky Way had formed like NGC 1277? What if our black hole had grown faster, devoured more, sterilized the galaxies sooner? There would be no Earth. No Sunday. No life. No us. It is a sobering reminder that the cosmos is not obligated to support life. That our existence is a consequence of a very specific set of conditions, and a great deal of luck. So when we look at NGC 1277, we're not just seeing a galaxy, we're seeing an alternate history. A reality where evolution halted early, where change was smothered by a monster at the heart of creation. And in that vision, we gain perspective. On our place. On our fragility. On the razor-thin margins that separate a galaxy filled with life from one filled with ghosts. As we continue exploring the enigmatic relic galaxy NGC 1277, our journey now turns toward one of the most profound questions it evokes. How exactly did this galaxy come to host a black hole so disproportionately massive? And why did that black hole seemingly dominate every aspect of its development from the very beginning? This question is not merely academic. It cuts to the heart of how galaxies and their central black holes grow together, a relationship that underpins much of modern astrophysical theory. And yet, NGC 1277 throws a wrench into that elegant picture, revealing a galaxy where the black hole appears to have consumed most of the available cosmic fuel before the rest of the galaxy had even finished forming. Let's imagine, for a moment, the early history of this galaxy, going back over 12 billion years, to an epoch when the universe was less than 2 billion years old. The universe was a much denser place back then, a seething stew of primordial gas, collapsing clouds, radiation, and the very first stars. Somewhere in this chaos, a particularly massive cloud began to collapse. The gas within didn't fragment into numerous small stars right away. Instead, it underwent what some models describe as direct collapse, forming a seed black hole possibly thousands, or even hundreds of thousands of times the mass of the Sun. What followed was a feeding frenzy. As gas continued falling in, this embryonic black hole began accreting matter at furious rates, converting gravitational energy into light and radiation. The accretion disk around it spun faster and faster, superheating as it spiraled inward. Jets of radiation and matter shot out along the poles, drilling through surrounding gas. This was a quasar phase, bright, violent, and brief by cosmic standards. And it may have lasted long enough for the black hole to swell to billions of solar masses while simultaneously sterilizing the inner regions of the forming galaxy. This early, unchecked growth of the black hole may explain the unique characteristics we see in NGC 1277 today. The galaxy's stars are ancient, compact, and devoid of gas, suggesting that the black hole's activity essentially choked off further star formation before it could fully take root. The black hole didn't merely form at the center of NGC 1277, it likely dictated the form that galaxy would take, compressing its potential into an ultra-compact spheroid of old stars and stifled futures. But there's something even more fascinating to consider. NGC 1277's black hole may have stopped growing billions of years ago. Its present silence, no bright quasar, no large accretion disk, no dramatic jets, suggests that the fuel needed to sustain its activity has long been exhausted. It sits now as a dormant behemoth, a fossilized remnant of an ancient cosmic battle. And that's significant, because while it no longer feeds actively, it still warps the space around it, governing the movement of stars at its core and subtly shaping the galaxy's internal dynamics. From an observational standpoint, the evidence for this black hole's mass comes from precise measurements of stellar velocities near the galactic center. These measurements, taken using high-resolution spectroscopy and adaptive optics, reveal extreme gravitational influence, stellar orbits so tight and fast that only a supermassive black hole can account for them. While there was initial skepticism in the astrophysical community about the measurements, with some suggesting the black hole might be smaller, follow-up observations have consistently reaffirmed the monstrous mass estimate. Now consider this. In the traditional framework of galaxy formation, black hole mass and galaxy mass are tightly correlated. This correlation, known as the M-sigma relation, is thought to arise from the coevolution of galaxies and their black holes, with feedback processes ensuring that one doesn't grow significantly faster than the other. But NGC 1277 shatters this relation. Its black hole is too big for its galaxy, by at least an order of magnitude. It doesn't just sit outside the norm, it challenges the norm's very validity. This leads to theoretical conundrums. How common were galaxies like NGC 1277 in the early universe? If many such black hole first systems existed, why do we see so few relics today? Did most of them evolve into larger ellipticals through mergers, obscuring their origins? Or was NGC 1277 a fluke, the result of a rare convergence of mass, spin, gas flow, and environmental conditions that made such a formation possible only once in a billion galaxies? There's also the issue of dark matter. Galaxies, including NGC 1277, are believed to reside within massive halos of invisible dark matter that help bind them together gravitationally. Some studies suggest that NGC 1277 may have a lower than expected dark matter content, particularly in its inner regions. This is puzzling, because dark matter is thought to be essential for galaxy formation. If NGC 1277 truly lacks a dense central dark matter halo, it may suggest that its early development was even more unique and possibly more rapid than previously imagined. Perhaps it formed in a high-density region of the early universe where baryonic, normal, matter was unusually concentrated relative to dark matter. Alternatively, the apparent lack of dark matter may be an observational artifact, something skewed by the galaxy's extreme compactness or the assumptions built into our models. Either way, it represents a compelling mystery. How can such a massive, compact object exist without the expected scaffolding of dark matter that theory demands? Now let us widen the lens, stepping back from NGC 1277 itself to consider the broader implications of its existence. This single galaxy may hold the key to unlocking an entire class of ancient galaxies, known as compact massive galaxies, CMGs, that populated the early universe but seemed to disappear in later epochs. For decades, astronomers have wondered what happened to them. Did they simply grow through mergers into modern elliptical galaxies? Or did some of them, like NGC 1277, survive intact, hidden among the noise of more active, evolved galaxies? If relics like NGC 1277 are more common than we think, just hard to identify, then we might be looking at a cosmic time capsule that has preserved not just the history of one galaxy, but an entire era of galactic formation. By studying these relics, we could refine our understanding of how galaxies grew, how feedback from black holes shaped their development, and how the early universe operated under conditions vastly different from those we see today. And yet, the story of NGC 1277 isn't just about astronomy, it's about philosophy. In its silence, in its refusal to evolve, this galaxy speaks volumes about the nature of existence. It reminds us that not all paths lead to complexity. That some systems form fast, burn hot, and then fall silent, frozen in time. It stands in stark contrast to the Milky Way, with its spiral arms, ongoing star formation, and life-bearing planets. It is a ghost galaxy, not in the supernatural sense, but as a relic that haunts our models of cosmic development. NGC 1277 also invites us to reconsider the nature of cosmic longevity. Is it better, in a galactic sense, to grow slowly, evolving over billions of years, forming stars and planets and potentially life? Or is there a brutal efficiency in doing it all at once, forming a massive core, growing a supermassive black hole, and burning through all your fuel in the universe's youth? These are not questions science alone can answer. They require perspective, imagination, and even a sense of humility. Because NGC 1277 is more than a galaxy. It's a message from the past. A monument to the violence, beauty, and fleeting nature of creation on a cosmic scale. It is not like us, but in understanding it, we come to understand ourselves. Let us now delve deeper into the profound implications that NGC 1277 holds for our understanding of the universe, not merely in terms of its physical parameters or exotic anomalies, but in what it reflects about cosmic evolution, galactic sociology, and the mysterious behavior of matter and energy under the crushing influence of gravity over epochs too vast to truly comprehend. NGC 1277 is not merely an outlier in our astronomical databases. It is a cosmic confession, revealing that the universe does not always follow the tidy rules we've constructed to interpret it. To begin, we must emphasize just how startling NGC 1277's black hole really is. At approximately 17 billion solar masses, this one object accounts for roughly 14% of the galaxy's total mass. This is a staggering deviation from the expected ratio, which in most galaxies falls between 0.1% and 0.5%. For context, the supermassive black hole at the center of the Milky Way, Sagittarius A, weighs in at about 4 million solar masses, just a tiny fraction of our galaxy's total mass. NGC 1277, by contrast, appears to have allocated a major portion of its cosmic budget to a single point of gravitational collapse. This makes astronomers ask, how could such an extreme imbalance occur? What mechanisms could form a galaxy whose central black hole outweighs not only all expectations, but also the very environment that gave birth to it? The prevailing answer lies in violent, rapid formation events early in cosmic history, cataclysms that seeded this galaxy with potential, but also cursed it with premature stasis. Galaxies are not formed all at once, but through a process of hierarchical merging and gas accretion that can last billions of years. But what if NGC 1277 sidestepped this process by collapsing almost entirely in a single explosive event? Such a scenario might be traced back to an extremely dense region of the early universe. In a patch of overpressured space, where dark matter halos formed earlier and more violently than their surroundings, a proto-galaxy might have rapidly assembled from collapsing gas clouds. The high density and gravitational forces could have enabled a direct collapse black hole to form, one that skipped the intermediate stages involving supernovae and star clusters and jumped straight from gas cloud to black hole. Such a mechanism, while still under theoretical investigation, could explain the appearance of massive black holes very early in cosmic history. But the story doesn't stop at formation. We must also ask what happened afterward. Why didn't NGC 1277 evolve? Why didn't it grow larger, develop spiral arms, continue forming stars, or merge with other galaxies? The answer may lie in its environment. NGC 1277 resides in the Perseus cluster, one of the most massive structures in the nearby universe. Galaxy clusters are not gentle places. They are turbulent, crowded, and often stripped of the cold gas needed to form new stars. If NGC 1277 was unlucky, or perhaps lucky enough, to have been trapped within such a cluster early in its life, it may have experienced a process known as ram pressure stripping. This violent mechanism, caused by a galaxy plowing through the hot, diffuse gas that permeates a cluster, can tear away its cold gas reservoir, effectively quenching any further star formation. That means NGC 1277 could have been locked into its compact, red, dead state very early on, cut off from the nourishment needed to evolve into something more familiar. It became, in a way, a cosmic fossil, preserved not in amber, but in gravitational memory and the quiet hum of its ancient stars. Yet even in death, this galaxy is not still. It rotates fast. In fact, NGC 1277 spins at tremendous speeds, indicating a past filled with kinetic energy and dense rotational dynamics. This is another clue that its formation was fast and furious. High rotational velocity in compact galaxies implies a very rapid collapse, where angular momentum wasn't given time to dissipate. Unlike modern elliptical galaxies, which tend to form through slower mergers and thus spin more slowly, NGC 1277's dynamism betrays its primordial intensity. And this raises another fascinating question: how many galaxies like NGC 1277 are out there? Until recently, astronomers believed these ultra-compact, red, high-mass galaxies existed only in the early universe. Telescopes peering into deep space frequently identify red nuggets, at high redshifts, small, dense galaxies with old stellar populations that seem to vanish as the universe evolves. It was assumed they merged with other galaxies and grew into the larger ellipticals we see today. But if NGC 1277 has remained unchanged for billions of years, perhaps others have too. Perhaps some red nuggets have survived the chaos of galactic evolution by being in the right, or wrong, place at the right time. This has sparked a renewed hunt for relic galaxies, cosmic holdouts that provide a window into the ancient past without the distortions of time and distance that plague our view of distant galaxies. In fact, recent surveys have identified a few more candidates. They are rare, but they exist: dense, old, compact galaxies that defy expectations. Some lie in clusters like Perseus, others in relatively isolated environments. The more of them we find, the more we realize that our models may need revision. Galaxy evolution, it seems, is not a one-size-fits-all affair. This variability also reopens debates about the role of black holes in shaping galaxies. For years, the dominant theory held that black holes and galaxies co-evolve, that feedback from the black hole regulates star formation, ensuring a tight correlation between black hole mass and galaxy bulge mass. But NGC 1277, with its massive black hole and stunted galactic growth, suggests an asymmetrical relationship may be possible. What if black holes can outgrow their galaxies? What if feedback isn't always a regulatory process, but sometimes an overpowering one that halts galaxy growth entirely? Such scenarios challenge the very foundations of galactic astrophysics. They imply that our universe may be home to more exotic pathways than previously imagined, pathways where gravitational monsters are born first, devour their surroundings, and leave only husks in their wake. And speaking of devouring, while NGC 1277 is nicknamed the galaxy that eats other galaxies, the irony is that it may not have cannibalized many neighbors at all. Its growth appears to have halted early, and it bears few signs of having undergone major mergers. Its mass and structure suggest that it hasn't changed significantly in billions of years. So why the nickname? It likely comes from a combination of its giant black hole, its ravenous early phase, and the evocative drama of a galaxy so dominated by gravity that it seems poised to consume everything within reach. Even now, the stars closest to its center orbit at breakneck speeds, circling a gravitational abyss with escape impossible. And if a stray globular cluster or satellite galaxy wandered too close, there's little doubt that NGC 1277's central black hole would dismantle it without mercy. This black hole, by the way, isn't just big, it's potentially spinning at incredible speeds. Though difficult to measure directly, the angular momentum of such a beast influences the spacetime around it, twisting the very fabric of the universe and generating immense relativistic effects. If we could observe it up close, we might see frame dragging, gravitational lensing, and time dilation so severe that seconds near its edge would stretch into hours for outside observers. It's difficult to overstate the cosmic drama at play here. NGC 1277 is like a frozen explosion, a galaxy that burned brightly in its youth, consumed all it could, and now rests in silence, a heavy scar on the universe's memory. It is an astrophysical enigma, a monument to unbalanced formation, and a lesson in the unpredictable outcomes of cosmic evolution. And perhaps, most provocatively, it is a reminder that the universe does not owe us symmetry or elegance. It does not need to conform to our neat diagrams or predictive models. Sometimes it builds monsters. Sometimes it lets those monsters sleep. And so, as we continue to unravel the vast and silent tale of NGC 1277, we find ourselves standing at the crossroads of cosmology, astrophysics, and the philosophy of existence. It is not merely the mass of its black hole or the velocity of its stars that fascinates us. It is the questions it raises, the conventions it defies, and the silence it keeps across the unimaginable gulfs of time. When scientists first discovered this galactic anomaly, there was disbelief. A black hole that defied all scaling relations? A relic galaxy that hadn't aged, hadn't evolved, hadn't danced the long and winding waltz of mergers and rebirths that shaped the rest of the cosmos? It almost seemed too pristine, too preserved, too perfect to be real. But real it is. Verified by multiple observations, modeled with precise kinematic data, and studied with the best tools of modern astronomy. This verification process began with long-slit spectroscopy and high-resolution imaging, capturing the velocity dispersions of stars and mapping out the gravitational footprint left by the galaxy's unseen mass. Later, adaptive optics and integral field spectroscopy with instruments like the Gemini North Telescope helped confirm the behemoth black hole at its center. No longer was NGC 1277 an abstract curiosity. It was an irrefutable reality, staring us in the face with all the quiet might of ancient gravity. The age of its stars further contributes to the enigma. Spectroscopic analysis indicates that they are more than 10 billion years old. That puts their formation near the end of the epoch of reionization, when the universe was transitioning from opaque to transparent, from chaos to order. These stars are fossils themselves, stellar relics formed during a period when the cosmic web was just beginning to braid itself into the great structure of filaments and voids we see today. There are few galaxies whose stellar populations are so uniformly ancient. Most galaxies host multiple populations of stars, young, middle-aged, and old, each telling a different chapter in a galaxy's saga. But not NGC 1277. Here, the story seems to begin and end within a narrow band of time, frozen shortly after the Big Bang. This singular characteristic is crucial to the idea of a relic galaxy. NGC 1277 never got a chance to refresh itself with new star formation or to engage in rejuvenating mergers that stir up interstellar gas. Instead, it was arrested in its development, like a museum exhibit of galactic infancy. And while the galaxy itself is compact, its central black hole could reshape everything we know about galactic evolution. Black holes of such size and density are typically found at the hearts of massive ellipticals, giants like M87 or IC 1101, which have undergone thousands of collisions and cosmic entanglements. Yet NGC 1277 sits there, a mere 240 million light-years from Earth, with a diameter of just 10 kiloparsecs, and a central mass that outweighs the Milky Way's central black hole by a factor of several thousand. It's as if a bonsai tree bore the roots of a redwood. What does this say about our cosmic narrative? Perhaps that it is not linear. That size is not always destiny. That history can play favorites, or monsters. There are hypotheses that suggest NGC 1277 could have once been part of a larger structure and lost its outer halo in a tidal encounter, leaving only the hardened, bulge-dominated core behind. But this theory doesn't fully account for the sheer mass of the black hole or the uniform age of its stars. Others argue it never merged with anything at all, defying all statistical likelihood. Either way, it is not what we expect a galaxy to be. It is what it is, and that makes it profound. Its orbit within the Perseus cluster also adds an additional layer to this mystery. Clusters are graveyards of galactic dreams. They contain thousands of galaxies, all moving at high speeds, in a hot bath of plasma that can strip them bare and silence their ability to give birth to stars. NGC 1277 orbits near the center of the Perseus cluster, a hostile environment ruled by tidal forces and gravitational interactions. Any attempt it might have made to grow was likely thwarted by the cluster's harsh physics. It was, quite literally, caged before it could evolve. Yet even in its cosmic prison, it demands attention. The presence of NGC 1277 within such a populated region may explain its solitude. It's a relic, not just because it is old, but because it has been protected from change by circumstance. Surrounded by violent neighbors and starved of gas, it lived in quarantine, a galactic hermit bearing secrets too ancient to forget. In recent years, theoretical astrophysicists have begun to reconsider how such galaxies fit into the broader picture of structure formation. Simulations from projects like Illustris and Eagle are beginning to include these outliers in their statistical frameworks. Yet no simulation to date has perfectly replicated a galaxy like NGC 1277. Either the black holes don't grow that big, or the galaxies don't stay that small, or the conditions that create such relics vanish in subsequent epochs. The fact that we've found one, or perhaps a handful, means either our simulations need refinement, or our assumptions need to be challenged. Let us imagine, for a moment, the scale of what NGC 1277 represents. Picture it as a singularity not just in terms of mass and gravity, but in knowledge. A black hole of understanding, a dense knot where our theories fall inward, unable to escape without being reshaped. This galaxy is more than a number on a chart or an outlier in a graph. It is a mirror held up to our assumptions, showing us not what is probable, but what is possible. We often describe the universe in terms of averages. The average mass of a star. The average lifespan of a galaxy. The average rate of star formation across cosmic time. But NGC 1277 laughs at averages. It is a cosmic outlier, a rebel that defies statistical smoothing. And in that rebellion lies its power. If we view NGC 1277 not as an aberration but as a window, we must ask, what lies beyond it? Are there more galaxies like it, hiding in the dark, tucked within clusters or forgotten corners of the cosmos? Do they speak of an ancient order, one that predates the universe we think we know? If so, then NGC 1277 may not just be a galaxy. It may be a remnant of an older blueprint. A prelude to the current act. A whisper from the dawn of structure itself. In time, the James Webb Space Telescope and other next-generation observatories may give us clearer answers. They may peer into the deep, into the edge of the observable cosmos, and find red nuggets preserved by cosmic coincidence. They may find galaxies that formed early, formed fast, and never changed, each one a potential sibling of NGC 1277, echoing across billions of light years. And maybe, just maybe, this black hole-powered relic will no longer be alone. As our journey through the mysteries of NGC 1277 continues, the cosmic silence surrounding this ancient galaxy grows louder. This relic does not shout with bursts of supernovae or blaze with the heat of newborn stars. It whispers, quietly, steadily, and enduringly, about an era we barely understand. And in those whispers lie clues not just to the nature of galaxies, but to the very structure of the universe and the laws that govern it. One of the most startling revelations about NGC 1277 is how it challenges the established black hole galaxy scaling relations. These empirical relationships, between a galaxy's bulge mass, velocity dispersion, and its central black hole, have formed the cornerstone of modern galactic astrophysics. They suggest that black holes and galaxies grow together, influencing each other through feedback loops over billions of years. But NGC 1277 simply does not fit. It is like discovering a child with the heart of a giant, a paradox that defies nurture and nature alike. This has prompted astrophysicists to question the universality of those relationships. Could there be two separate populations of galaxies, those that follow the standard coevolutionary path, and those like NGC 1277, which formed their massive black holes rapidly and then essentially went dormant? If that is the case, the diversity of galactic formation and evolution is far greater than we ever imagined. It could mean that our models are not merely incomplete, they might be based on assumptions that are valid only in limited contexts. NGC 1277 reminds us that the cosmos is not obligated to follow our neat equations. But what could possibly explain such an oversized black hole in such a compact galaxy? One possible explanation involves gas-rich, high-redshift galaxies known as red nuggets. These were dense, elliptical galaxies that formed early in the universe's history, around redshift C2, and then faded as star formation halted. NGC 1277 may be a direct descendant of one such red nugget, preserved across eons due to environmental isolation. While many red nuggets were cannibalized in galactic mergers or grew into large elliptical galaxies, NGC 1277 somehow avoided this fate. It remained small. It remained pure. It remained unchanged. Another theory suggests that its black hole grew rapidly in the early universe through a combination of direct collapse mechanisms and runaway accretion. Perhaps in the turbulent conditions of the early cosmos, an immense reservoir of gas funneled into the center of a protogalaxy, birthing a monster black hole before feedback mechanisms could kick in to slow it down. In this scenario, NGC 1277 is a fossilized relic of those chaotic times, a snapshot of runaway galactic development arrested in progress. Its stars, too, hold secrets. Spectral analysis shows they are alpha-enhanced, meaning they are rich in elements like oxygen, magnesium, and silicon, which are produced in Type II supernovae, the explosions of massive stars. This indicates that NGC 1277 underwent a short, intense burst of star formation early in its life, one that was rapidly quenched before Type I supernovae could contribute iron. This rapid chemical evolution reinforces the idea of a violent youth followed by a long, quiet adulthood. It also deepens the mystery. Why did star formation shut down so quickly? What mechanism expelled or consumed all the gas in such a short time? Was it the black hole itself, whose energy output could have sterilized the galaxy, preventing further star formation? If so, NGC 1277 may be a case study in the power of black hole feedback. The very heart of the galaxy, the engine that might have nurtured growth, could also have been its executioner. As astronomers dig deeper, they also explore the dynamics of the stars within the galaxy. Unlike spiral galaxies with organized disks of stars orbiting in unison, NGC 1277 exhibits high-velocity dispersion. This means its stars move rapidly in random directions, a characteristic of elliptical galaxies where gravitational equilibrium is maintained by random motion rather than coherent rotation. These measurements offer additional evidence of its compact and dense structure, where the influence of the black hole reaches far into the galaxy's stellar population. And let us not overlook the role of dark matter. While dark matter is known to play a crucial role in the formation and stability of galaxies, NGC 1277 appears to be surprisingly deficient in it, at least in its inner regions. Studies using kinematic modeling suggest that its visible mass accounts for almost all the gravitational effects observed within its compact frame. This unusual lack of central dark matter has led to further questions. Was it stripped during interactions with the Perseus cluster? Or did the galaxy form in a rare, low dark matter halo? Or, in the most speculative vein, does NGC 1277 point to new physics, a flaw in our understanding of gravity on galactic scales? All of these questions reinforce why this galaxy matters so deeply to astronomers. It is not just a relic, it is a rogue data point that challenges the scaffolding of modern cosmology. If a galaxy can form a black hole this massive without growing proportionally, then the processes that shape the universe may be more stochastic than deterministic. Chaos and coincidence may play larger roles than we have been willing to admit. And what of the black hole itself? Estimated at around 17 billion solar masses, it is one of the largest ever discovered. If placed at the center of the Milky Way, it would swallow the solar system whole, stretching from the Sun to Pluto and beyond. Its gravitational radius is so large that light could take days to traverse its event horizon. Yet it sits in the center of a galaxy only a fraction of the size of the Milky Way, content, dormant, and silent. There is no evidence of accretion, no powerful jets, no blinding radiation, no tidal disruption flares. It simply sits there, invisible but unmistakable, a monument to an age long past. Such stillness is haunting. We are used to associating massive black holes with luminous quasars or energetic AGN. But this one rests quietly. Perhaps it exhausted its fuel long ago. Or perhaps the conditions of the Perseus cluster deny it further sustenance. This black hole also forces us to reconsider the role of these objects in the history of the universe. We often think of black holes as endpoints, of stars, of matter, of time. But perhaps they are also beginnings. Perhaps this one formed not as a result of the galaxy's growth, but as its catalyst. If so, we may need to invert our diagrams, to redraw our arrows of causality. The black hole did not arise from the galaxy. The galaxy may have arisen from the black hole. And what does this mean for us here, on our quiet little rock in the outer spiral arm of a relatively modest galaxy? It means that the universe is capable of extremes we are only beginning to grasp. It means that for every elegant theory, there is an exception that waits in the dark. It means that truth, like gravity, often hides at the center, silent, unseeable, yet inescapable. As we move forward, armed with better telescopes and deeper surveys, we may find more galaxies like NGC 1277. Or we may find none. It may be unique, a freak, a fossil, a message written in gravity and starlight across 10 billion years of time. But until then, it remains what it is, the galaxy that eats others, and yet hungers no more. A cosmic paradox. A contradiction wrapped in stars. A black hole that grew too big, too fast, and then stopped. A relic that remembers a time when the universe was young, wild, and full of fire. And so our odyssey into the heart of NGC 1277 continues, plunging deeper into the currents of cosmological speculation, astrophysical analysis, and the eerie silence of a relic that stands as a monolith to an early universe now lost to time. To understand the implications of this galaxy fully, we must widen our lens, not just look at what it is, but what it represents, what it suggests about the cosmos as a whole, and how it subtly but surely shakes the foundations of what we thought we knew. NGC 1277 exists in a kind of cosmic paradox. Its black hole is too large, its stars are too old, and its environment too hostile for the standard model of galactic growth. This makes it not only a fascinating object of study but also a scientific threat, a ghost of a reality that modern theories struggle to reconcile. When confronted with such anomalies, astronomers must often weigh two paths, either dismiss the object as an outlier, a fluke of probability, or consider the much bolder proposition that our understanding of the universe is incomplete. Let us examine this question more closely. What if NGC 1277 is not merely an exception, but part of a hidden population of galaxies that we have overlooked or misclassified? If these relic galaxies with massive central black holes are more common than assumed, our models of galaxy black hole coevolution need urgent revision. And if they are rare, then why did they fail to evolve like the rest of their peers? Was it an early isolation that froze their development, or a brief but extreme infall of matter that lit the black hole, formed stars, and consumed all available gas in one short, furious burst? As we peer further into the mechanics of NGC 1277, one thing becomes clear. This galaxy is not just a passive subject of observation, it is an active puzzle. Its lack of star formation for over 10 billion years is not just a historical fact but a mystery with no clear cause. Astronomers propose that the black hole's immense energy output in its youth may have heated and expelled all the gas needed to form new stars. This idea, known as quasar-mode feedback, posits that during the black hole's active phase, powerful winds and jets of radiation sterilize the galaxy. It's a cosmic self-sabotage. The engine that built the galaxy also ensured its stagnation. This concept is mirrored in computer simulations like Illustris and Eagle, where feedback from central black holes often halts star formation in massive galaxies. However, NGC 1277's case is extreme. It halted star formation very early and never resumed, never merged, never reignited. It is the celestial equivalent of a brilliant flame snuffed out too soon. That flame, however, left behind a remnant whose mass alone defies statistical logic. From a dynamical perspective, the black hole's influence in NGC 1277 is profound. In most galaxies, the black hole's gravitational sphere of influence, the region where its pull dominates over that of the stars, is relatively small. But in NGC 1277, this sphere extends much further than expected, affecting stellar orbits far from the center. This warps the kinematics of the entire galaxy, inducing abnormally high velocity dispersions. Observational data shows stars whipping around at over 300 km per second, an extreme figure for a galaxy of this size. These motions, mapped through adaptive optics and spectral line analysis, tell a story of intense central gravity and long-term stability, devoid of major disturbances. Such measurements are not easy. They require powerful instruments like the Hubble telescope and the Gemini North telescope. Using integral field spectroscopy, astronomers can obtain spatially resolved velocity maps, tracking how stars move at various points in the galaxy. The data are then fit with complex dynamical models to estimate the mass distribution. In NGC 1277's case, the result is always the same: the black hole is too big. Every time, it exceeds expectations by an order of magnitude. And what of its location, at the outskirts of the Perseus cluster? This environment adds another dimension of intrigue. Galaxy clusters are violent arenas where galaxies frequently interact, merge, and strip gas from each other. Yet NGC 1277 appears untouched, as though preserved in a cosmic museum. How has it avoided the fate of its neighbors, which show signs of mergers, tidal tails, and active star formation? Perhaps its orbit through the cluster kept it at a distance, or perhaps its internal structure and density made it resistant to tidal disruption. It is as if NGC 1277 found a way to survive without evolving. In this way, it mirrors the concept of a passive galaxy, but pushed to the extreme. Most passive galaxies still undergo minor mergers, accrue mass slowly, or experience bursts of residual star formation. NGC 1277 does none of this. It is an isolated, compact, and completely inert object. Not even globular clusters or extended stellar halos mark its presence. It is a cosmic fossil, locked in time. This fossil-like nature opens another line of investigation: whether NGC 1277 can be used as a standard benchmark for understanding the early universe. In the absence of dynamic changes, its chemical composition and stellar populations have remained relatively unaltered. This makes it a clean testbed for theories of chemical enrichment and stellar evolution. Astronomers can study its spectral lines to determine the abundance of elements like magnesium, oxygen, and iron, which provide insight into the types of supernovae that enriched its gas. From this, we learn not only about NGC 1277 itself, but about the conditions of the universe when it formed. Furthermore, the galaxy's compactness draws attention to the broader population of compact massive galaxies, or CMGs, found at high redshift. These galaxies, identified in deep surveys like Cosmos and Candles, are small, dense, and old, just like NGC 1277. Many have disappeared, likely subsumed into larger systems through mergers. But NGC 1277 remains. It is the living descendant of these CMGs, and studying it allows us to understand what might have become of them had they survived unaltered. Even the dark matter debate intensifies in NGC 1277's presence. Most galaxies are dark matter dominated at large radii, but NGC 1277's inner regions appear almost devoid of it. This finding has been confirmed by multiple teams using different methods. The implication is either a strange formation history, perhaps the dark matter halo was stripped, or a challenge to our understanding of dark matter distribution. Either way, it casts a long shadow on assumptions we make about cosmic structure formation. Then comes the philosophical question, the one that echoes in observatories and lecture halls alike: how much can we generalize from the outlier? If NGC 1277 is one of a kind, is it a curiosity or a harbinger? Should it be the exception that proves the rule, or the exception that rewrites it? In science, outliers often lead to revolutions. They force recalibration, inspire new models, and reveal unseen variables. In this sense, NGC 1277 is not just a galaxy. It is a question posed to the universe. And that question is a profound one. What if the fundamental processes that govern galaxy formation are not as universal as we thought? What if the diversity of galactic life histories is far greater than our simulations can yet accommodate? What if the cosmos is a chaotic landscape where multiple formation pathways lead to wildly different outcomes? In the face of NGC 1277, we are reminded of how young our science is. The sky is full of secrets, and we have only just begun to listen. This sense of cosmic humility, born from the stark presence of NGC 1277, reverberates through every facet of astrophysics. We are no longer observers merely cataloging the heavens. We are detectives, piecing together clues from a crime scene billions of years old, where the laws of gravity, energy, and matter have performed a dance so intricate and ancient that even our most sophisticated models sometimes stumble. Consider the implications for black hole growth theory alone. Traditionally, supermassive black holes are thought to grow in tandem with their host galaxies, a relationship encoded in the well-established M-sigma relation, the observed correlation between the mass of a black hole and the velocity dispersion of stars in the galactic bulge. NGC 1277 laughs in the face of this relation. Its central black hole is around 14% of its total stellar mass, an order of magnitude greater than the 0.1% to 0.5% typically observed. This galaxy does not just deviate from the trend, it utterly breaks the curve. One possibility is that we are seeing a different mode of galaxy formation altogether, one in which the black hole formed first, rapidly and violently, in the very earliest epochs of the universe. If that is true, then NGC 1277 may be a relic not just of a galaxy but of an era, a primordial environment where gas collapsed directly into a black hole before significant stellar formation occurred. The galaxy that followed would have been shaped around the already formed behemoth, stunted by its intense feedback and limited access to cool gas. In this context, NGC 1277 might be offering a glimpse into what astronomers call direct collapse black holes, massive black holes that formed without the intermediary step of star formation. These are believed to be the seeds of the most massive black holes in the universe, but very few candidates have ever been observed. Could NGC 1277's black hole be one of these rare seeds that simply stopped growing? Could it be the last remnant of a galactic template that failed to catch on, yet managed to endure? This hypothesis dovetails with another curious attribute of NGC 1277, its complete lack of cold gas. Cold molecular hydrogen is the raw material for star formation, and its presence usually correlates with young stellar populations. But in NGC 1277, observations using the IRAM 30M telescope and ALMA have shown an almost total absence of such gas. Its interstellar medium is inert, and there are no signs of ongoing or recent star formation. It's as though the galaxy exhaled its last breath eons ago, and now floats as a spectral echo of what might have been. Even its color betrays its age, reddened not by dust but by time. The stars within NGC 1277 are overwhelmingly old, with estimates placing their ages at over 10 billion years. These are the relics of a time when the universe was a quarter of its current age, when galaxies were smaller, more chaotic, and dominated by rapid processes. By studying the spectral energy distribution of this ancient stellar population, we can infer the star formation history of NGC 1277, which paints a picture of a sudden burst followed by near-total silence. Such a burst would have required enormous gas reservoirs, likely gathered during a time when the universe was dense and ripe for collapse. Perhaps NGC 1277 formed in a special location within a primordial filament of the cosmic web, where gravitational convergence was strong and matter inflow rapid. This would have allowed the galaxy to build up mass quickly, and then seal itself off from the outside world. If this is true, then NGC 1277 is a fossil not just of a galaxy but of a region of the early universe, a point of unique confluence where conditions briefly allowed something extraordinary to occur. Its isolation within the Perseus cluster only deepens the mystery. How did it avoid further evolution in such a crowded environment? Why did it not merge with neighboring galaxies, absorb gas, or become gravitationally perturbed? Some simulations suggest that compact galaxies like NGC 1277 might orbit on the periphery of clusters, avoiding dense central regions and thus sidestepping the violent interactions that trigger growth. Others propose that its high velocity within the cluster effectively shields it from accretion, as it passes through potential sources of gas and stars too quickly to capture them. This notion of high-speed travel through a dense cluster environment introduces another interesting phenomenon: gravitational stripping. Galaxies moving rapidly through a cluster can lose their outer dark matter halos through tidal interactions, leaving behind a compact, baryon-dominated core. Could NGC 1277 be the core of a once larger galaxy, whittled down by countless orbits through the Perseus cluster? If so, its current appearance is not just a snapshot frozen in time but the result of cosmic sculpting, an ancient object eroded by gravitational tides until only its densest regions remain. This possibility aligns with measurements of its dark matter content, or rather, the conspicuous lack thereof. Numerous dynamical models and rotation curve analyses indicate that NGC 1277 has very little dark matter, at least within the regions probed by current instruments. This could be because the dark matter was stripped away during its travels, or it could mean that it never had much dark matter to begin with, perhaps forming in a way that concentrated baryonic matter in the center while leaving dark matter diffuse. Each of these scenarios points to a different and equally profound conclusion. If NGC 1277 was once large and lost mass, it challenges our understanding of cluster dynamics and galactic resilience. If it was always compact and dense, it challenges our understanding of galaxy formation and black hole seeding. And if it formed its black hole before its stars, it rewrites the very sequence of cosmic events that astronomers have long taken for granted. Adding to this conundrum is its mass-to-light ratio, which is higher than average. This is another hallmark of an old stellar population dominated by red and low-mass stars. The result is a galaxy that looks dimmer than it really is, hiding its mass behind a veil of faint starlight. It is a perfect camouflage, one that might explain why more galaxies like NGC 1277 haven't been identified. They could be hiding in plain sight, their relic cores overlooked in favor of brighter, more active targets. This leads to a new frontier in extragalactic astronomy, the search for analogs. Could there be other relic galaxies out there, silently drifting through space, their ancient hearts beating beneath the noise of the cosmos? Some candidates have emerged, including objects like MRK 1216 and PGC 032873. These galaxies share some of NGC 1277's traits: compact size, high velocity dispersions, overmassive black holes, but none quite match its extremity. NGC 1277 remains the archetype, the standard bearer, the one true anomaly that refuses to fit any mold. The implications of finding more relics like NGC 1277 are enormous. It would allow for population studies, which in turn could be used to refine or overthrow current formation models. It would mean that the early universe was even more diverse and chaotic than we thought, and that the fingerprints of its turmoil are still etched into the quiet corners of today's cosmos. It would mean that the one-size-fits-all approach to galaxy evolution must be abandoned in favor of a multi-threaded narrative, where different paths lead to different fates, and where outliers are not exceptions but chapters in a longer, more complex story. It speaks across time, not in words, but in mass and motion, in stellar light and silence, in the yawning gravity well at its core. What it tells us is that the universe is not governed solely by the neat timelines and predictable hierarchies we construct, but by a chaos far older and more intricate than we have dared to imagine. It tells us that some galaxies formed quickly and burned out just as fast, others took eons to grow, and some, like itself, were born with an ancient heart that refuses to die. In its quiet defiance, NGC 1277 opens 1,000 new questions. Was it always alone, or did it once have companions? Could it have been part of a galactic family, slowly cannibalized by cluster dynamics, leaving this lone survivor behind? Or did it form in solitude, a monastic object in a screaming universe, protected by happenstance and physics from the chaos around it? To seek answers, we turn to simulations, those vast computational experiments in which galaxies evolve in artificial universes. The illustrious and Eagle projects have modeled the evolution of thousands of galaxies, yet finding analogs to NGC 1277 has proven difficult. Their rarity in simulations is either a limitation of the resolution or a sign that the formation of such galaxies requires conditions not commonly included in the models, perhaps feedback mechanisms or early dark matter behavior that we do not yet fully understand. Some astrophysicists suggest that NGC 1277 is the result of a collapsed high sigma density peak in the early universe, a region of space so overdense that it quickly became gravitationally unstable and collapsed in on itself. This would produce a rapid infall of matter, both baryonic and dark, potentially forming a massive black hole at the center before star formation could begin. If this theory holds, then NGC 1277 is the result of a cosmic accident that occurred in the universe's first billion years, an anomaly born from probability tails and quantum fluctuations that were frozen into the structure of space-time during cosmic inflation. And then there's the psychological layer, the sheer awe that NGC 1277 instills in those who study it. There's something deeply poetic about a galaxy that defied time and transformation. It is an unchanging sentinel amidst a sea of change, a cosmic ghost ship that sails through space, its decks empty, its engines cold, its story long since written. And yet, it speaks to us. Its every orbital velocity, every absorption line in its spectrum, every arcsecond of its compact frame tells us. This is what was. This is what could have been. This is what still might be. From the perspective of cosmic archaeology, NGC 1277 is a Rosetta Stone. By analyzing the chemical composition of its stars, we can deduce the metallicity and abundance ratios, which offer clues about the types of supernovae that exploded within it and how quickly they occurred. Current data indicates that its stars are alpha-enhanced, a telltale sign that the bulk of its stellar mass was formed in a very short time frame dominated by Type II supernovae, with minimal contribution from the slower Type I explosions. This compression of enrichment timescales implies a starburst that lasted only a few 100 million years, shorter than the entire formation time of the Milky Way's thin disk. Its lack of a disk is another clue. Most galaxies, even ellipticals, show remnants of a flattened component, the vestige of rotational dynamics. NGC 1277, by contrast, is nearly isotropic in shape and motion. Its stars move in randomized orbits, with little sense of a preferred direction. This suggests a formation process that was more violent than elegant, more collapse than accretion, more explosion than rotation. It's as if the galaxy never had the time, or the gas, to settle into a disk before its fate was sealed. Further deepening the enigma is the possibility that NGC 1277 harbors not just a supermassive black hole, but a primordial one. This is a particularly speculative, though increasingly discussed, area of research. Primordial black holes are hypothetical objects that may have formed directly from density fluctuations in the early universe, before any stars, galaxies, or even atoms had formed. If some of these black holes were large enough, they could have served as the seeds around which early galaxies coalesced. NGC 1277's monster black hole, with its extreme mass and peculiar relationship to its host, could be such a relic. Even the mere suggestion of this opens up extraordinary possibilities. If NGC 1277 houses a primordial black hole, then it is not just a galactic relic, it is a pre-galactic one, a relic of a time when the universe was still a fog of plasma and light. Such an object would not only revolutionize our understanding of black hole formation but also offer insights into the very fabric of the early cosmos, the inflationary epoch, quantum fluctuation scales, the nature of dark matter and dark energy, and the possible existence of exotic fields or particles. To probe this possibility, future missions like the James Webb Space Telescope, JWST, the Extremely Large Telescope, ELT, and space-based gravitational wave detectors such as LISA will be crucial. With higher resolution and better sensitivity across a broader range of wavelengths, astronomers will be able to model NGC 1277 with unprecedented precision. Gravitational lensing could offer indirect measurements of its dark matter halo. Spectroscopic surveys could refine our understanding of its metallicity gradient. And if, somehow, it were to merge with another galaxy or black hole in the future, gravitational wave detectors might even capture the echo of its final song. Until then, we are left with mystery, and that, perhaps, is the most exciting part. Because NGC 1277 forces us to admit what we do not know. It humbles the astrophysicist and delights the poet. It's a galaxy that shouldn't exist, and yet does. A fossil that never fossilized. A ghost that refuses to fade. And in that quiet refusal lies a challenge, to look deeper, think broader, and accept that the universe is not a closed book of solved equations but an ever-evolving manuscript, written across light years in ink we are only beginning to decipher. The longer we stare into the dense heart of NGC 1277, the more its mysteries deepen rather than unravel. This isn't just a case of scientific curiosity. It is a full-blown cosmic puzzle that rewrites how we perceive the early epochs of galaxy formation and the very nature of black holes themselves. What makes NGC 1277 so hauntingly compelling is not just its mass or age, but its refusal to conform to the models that define our understanding of galactic evolution. Consider the paradox of galactic cannibalism. Most galaxies that grow abnormally large do so through violent mergers and tidal interactions, devouring smaller galaxies over billions of years. They become bloated giants, trailing stellar debris and hosting complex, multi-generational stellar populations. Yet NGC 1277 has done the exact opposite. Though it sits in a bustling cluster, Perseus, teeming with gravitational possibilities, it remains isolated in its composition. It has not grown through cosmic consumption. Instead, it is as though it swallowed its fate whole at the beginning of time and has remained sated ever since. How did this galaxy avoid the gravitational buffet that defines so many of its neighbors? There are multiple theories. One is orbital luck. NGC 1277's trajectory through the Perseus cluster might have shielded it from interactions with other galaxies. Unlike many of its neighbors, it may orbit in a path that has kept it far from major collisions. Its speed relative to the cluster could also play a role. If it is moving too fast, it would not be able to capture or merge with other galaxies efficiently. This flyby behavior, where a galaxy streaks past others too quickly to be caught, could explain why it hasn't acquired new stellar material in billions of years. Then there's the influence of its environment. NGC 1277 resides in a region dominated by the immense gravitational influence of the Perseus cluster, a massive collection of galaxies enveloped in a web of dark matter and hot intracluster gas. This hot gas acts like a furnace, stripping infalling galaxies of their own gas reservoirs in a process known as ram pressure stripping. A galaxy like NGC 1277, already dense and devoid of cool gas, would be immune to such a process, but it also means it wouldn't gain gas from other galaxies. In this way, the Perseus cluster could have acted both as a cradle and a cage, protecting NGC 1277 from external growth, while locking it into a state of suspended evolution. Moreover, the radiation environment of the cluster might have suppressed future star formation. High-energy X-rays and cosmic rays within the cluster medium may have prevented new gas from cooling and collapsing, choking off any potential for new stellar generations. This contributes to the galaxy's ancient appearance. It shines not with the brilliance of youthful stars, but with the dim, reddish glow of long-lived, low-mass stellar remnants. But the biggest revelation, the one that continues to spark debate and recalibration of theoretical models, is the black hole. NGC 1277's central black hole is not just large. It is staggeringly, grotesquely oversized. With an estimated mass of over 17 billion solar masses, it constitutes more than 14% of the galaxy's total stellar mass. That's nearly an order of magnitude greater than what traditional black hole scaling relations would predict. Why does this matter? Because in galactic astrophysics, we rely on certain rules to hold the black hole mass should scale with the bulge mass of the galaxy. This relationship, known as the M-sigma relation, is a foundational principle, guiding everything from simulation design to our expectations of cosmic evolution. NGC 1277 shatters that rule. It is the anomaly in the dataset. And such anomalies are not errors, they are revelations. They reveal the boundaries of our knowledge. They tell us that the M-sigma relation may not be universal. That black holes can grow wildly disproportionate to their host galaxies under certain extreme conditions. That, perhaps, in the earliest epochs of the universe, black holes could grow faster than the galaxies that house them, either through direct collapse of massive gas clouds, or via mechanisms that remain deeply hidden in the mathematics of relativity and quantum gravity. And yet, despite its gravitational ferocity, NGC 1277 is silent. There is no quasar activity, no jets erupting from its core, no broadline emissions or blazars lighting the sky. This suggests that its black hole, though monstrous, is currently dormant, starved of the infalling matter that would otherwise awaken it into a radiant beacon of high-energy chaos. In astrophysical terms, it's a sleeping dragon, a core of nearly infinite density and hunger, slumbering in stillness at the center of a galaxy that refuses to change. From a storytelling perspective, this paints NGC 1277 as more than just a relic. It becomes a kind of cosmic parable. A lesson about scale, time, isolation, and the extremes of natural law. In its stillness is a message that not all growth is linear, not all evolution continues forever, and that some things, whether through fate or physics, are born ancient and remain untouched by the hands of time. If we lived in the galaxy, we would experience the universe very differently. The density of stars in its compact core would mean a night sky filled with bright points of light, dozens, even hundreds of stars visible to the naked eye in close proximity. And yet these stars would all be old. There would be no brilliant, short-lived blue stars. No stellar nurseries. No gaseous nebulae. No possibility for planets forming anew. In this way, NGC 1277 is both spectacular and sterile, a breathtaking monument to what was, but never to what might be. For cosmologists and galactic dynamicists, studying NGC 1277 becomes a way to test the boundaries of simulation fidelity. It pushes us to revisit early universe conditions with new eyes. How did the baryonic matter collapse so efficiently to form such a dense stellar core without a rotating disk? What were the feedback mechanisms from early supernovae, and why didn't they blow apart the nascent galaxy? What role did cold gas flows, filamentary accretion, or high redshift halo interactions play in this frozen behemoth? Each of these questions is a rabbit hole, an entire field of inquiry. And the more we dig, the more the foundations of our understanding begin to quake. NGC 1277 reminds us of something fundamental. In astronomy, every anomaly is a treasure. Every contradiction is an opportunity. Every cosmic outlier is a doorway to a deeper, more profound layer of reality. As we push forward, through newer telescopes, finer simulations, and more refined theories, the mystery of NGC 1277 will continue to be a touchstone. It is the question mark at the end of an equation, the ancient stone in a modern machine, the rogue paragraph in a script otherwise bound by rules. And perhaps the most compelling idea of all? There may be more galaxies like NGC 1277, hidden in plain sight, mistaken for normal ellipticals, their secrets buried under dust, redshift, and misclassification. If we look hard enough, with the right tools and the right questions, we may find an entire subpopulation of relics, quiet titans from a forgotten age, scattered like fossils across the observable universe. Each one a relic. Each one a riddle. Each one a whisper from the beginning of time. Even as we peer into the heart of NGC 1277 with our most sophisticated instruments, whether it's the Hubble Space Telescope, adaptive optics systems on Earth-bound observatories, or the powerful insights gleaned from spectroscopic data, we are constantly reminded of how much we do not know. The moment we thought we understood elliptical galaxies, this object emerged as a counterexample so profound, it forced astronomers to question some of the most trusted models in cosmology and galactic evolution. Let us now imagine the early universe, some 10 to 13 billion years ago, a time dominated by chaotic, high-energy interactions, where matter swirled violently under the influence of gravity, and the rules of structure formation were being written in real time. In this infant cosmos, NGC 1277 appears to have formed rapidly, in what is often described as a monolithic collapse. Unlike modern galaxies, which gradually build up their mass through mergers and accretions, NGC 1277 may have formed almost instantaneously, as a compact blob of stars in a colossal burst of formation that then slammed shut like a vault. This is a radically different narrative compared to the standard hierarchical model of structure formation, which posits that galaxies form through the gradual accretion of smaller structures. But relic galaxies like NGC 1277 are the cosmic rebels, the exceptions that demand new models or adjustments to existing frameworks. This raises a profound question. Are galaxies like NGC 1277 relics of a lost age, or do they represent a parallel path of galactic evolution, one that is far rarer, more violent, and ultimately more isolated? Consider the role of gas. Gas is the raw material for star formation. In most galaxies, gas comes from a variety of sources: leftovers from the Big Bang, accreted from intergalactic filaments, or brought in during galactic mergers. Yet, NGC 1277 is almost completely devoid of cold gas. This raises the question, did it consume all its gas in that early burst of star formation, or was it somehow prevented from ever receiving more? Spectroscopic analysis shows that nearly all the stars in NGC 1277 formed over 10 billion years ago, in a time window no wider than 100 million years. This is like igniting an entire galaxy's worth of stars all at once, in a cosmic blink of an eye. Such a brief period of star formation implies incredible conditions: a high density of gas, efficient cooling, and probably intense gravitational collapse. Whatever conditions gave rise to NGC 1277, they were both rare and brief. The universe quickly moved on to other methods of building galaxies, but NGC 1277 remained, a frozen monument to this fleeting era. Now let's discuss the shape of the galaxy itself. NGC 1277 is extremely compact, with a diameter of roughly 10,000 light-years, about 1/10 the size of the Milky Way, yet it contains nearly as many stars. This compactness gives it an extreme stellar density, making it one of the densest galaxies known. Its shape is elliptical but more precisely described as lenticular, a smooth, featureless oval with very little structural detail. No spiral arms. No gas lanes. No central bar. No bulge disk separation. Just an oblong cluster of stars, like a jewel smoothed over by time. And then there's the rotation. Unusually for such a compact elliptical, NGC 1277 rotates rapidly, more like a spiral galaxy than a typical elliptical. This rotational behavior might be a relic of its original formation, where angular momentum was conserved even as its mass collapsed inward. It also suggests that not all of its early formation was chaotic. Some order persisted even during its turbulent birth, allowing it to spin rather than form a puffed-up, pressure-supported sphere. Let's return to the black hole, because it is impossible to overstate how bizarre and massive it is. To house a black hole this size, NGC 1277 would, by conventional scaling laws, need to be a much larger galaxy. And yet it isn't. This raises important questions about the coevolution of black holes and their host galaxies. Typically, we think that black holes grow in tandem with galaxies, each feeding off the other. But what if NGC 1277 is evidence that black holes can grow first, possibly even driving early galaxy formation? Some scientists have suggested a scenario where a primordial black hole, possibly formed in the earliest moments after the Big Bang, served as the seed around which the galaxy formed. Others argue that supermassive black holes can grow very quickly in dense regions of space, outpacing the rest of the galaxy's growth. In either case, the implication is stunning. The central black hole in NGC 1277 might be one of the first supermassive black holes to ever form, making it a truly primordial object. Even more intriguing is the idea that NGC 1277 could help us understand the early seeds of all black holes. If it formed in isolation and underwent no major mergers, then its current state is a direct fingerprint of early cosmic conditions. This makes it one of the purest test cases in the universe for studying how black holes and galaxies grow together, or separately. The silence of its central black hole is just as significant as its size. Astronomers initially expected to see strong X-ray emissions from the core. After all, a black hole of this mass should be actively accreting gas and lighting up the surrounding space. Yet observations found nothing. No strong emissions. No active galactic nucleus. This suggests the black hole is starved. Perhaps the galaxy's gas was expelled long ago, or never replenished. Without fuel, the black hole sleeps. And in that silence lies a warning: massive objects do not always announce themselves. Sometimes they wait. Sometimes they hide. Imagine a spacecraft approaching NGC 1277. The closer it gets, the more crowded the star field becomes. The density would rise dramatically, and the gravitational environment would become increasingly complex. Unlike our Milky Way, where stars are relatively spread out, the core of NGC 1277 would be suffocatingly full. Stellar collisions would be more common. Binary interactions would shape the orbits of entire clusters. And at the very center, the gravitational pull of the black hole would be so intense that stars orbiting close to it would whip around at incredible speeds, thousands of kilometers per second, creating what are known as relativistic stellar orbits. These stars, some moving in tight ellipses, others in nearly perfect circles, would offer us a laboratory for testing general relativity under conditions that are otherwise inaccessible. We could study time dilation, gravitational lensing, and perhaps even the behavior of dark matter near a massive singularity. In this sense, NGC 1277 is more than an ancient relic. It is a perfect experiment waiting to be observed, a cosmic particle accelerator running in slow motion across eons. And that brings us to the final, and perhaps most haunting, mystery of NGC 1277, its future. In the grand scheme of cosmic time, what happens to a relic? What happens to a galaxy that no longer forms stars, no longer merges, no longer evolves? Does it simply fade away, its stars aging into dim embers? Or does it one day awaken, triggered perhaps by a close encounter, a tidal interaction, or a sudden influx of gas? What would happen if NGC 1277 collided with a gas-rich spiral? Would it reignite? Would its black hole burst back into life, feeding on new material and launching jets into the void? Or is it too old, too set in its ways, too gravitationally inert to change course? And what about its black hole? Will it continue to grow, fed slowly by the occasional star that wanders too close? Or will it remain as it is, a silent giant, hidden at the heart of an ancient tomb? Whatever the answer, one thing is clear: NGC 1277 is not just a galaxy. It is a relic, a record, a riddle. It is a place where the rules we thought we understood fail. A place where time itself seems to have paused, waiting for us to ask the right questions. And as long as those questions remain unanswered, NGC 1277 will continue to haunt the skies, unmoving, unchanged, unforgettable. Let us now delve deeper into the haunting stillness of NGC 1277, this cosmic mausoleum that appears untouched by the chaos and churn of billions of years of cosmic evolution. In this suspended animation, one must ask, how has it avoided the fate of other galaxies? Why has it remained so pristine, unscathed by the ceaseless violence of the universe? To answer this, we must consider NGC 1277's environment, its place within the Perseus cluster, one of the most massive known clusters of galaxies. The Perseus cluster is a teeming metropolis of celestial bodies, rich in intergalactic gas and roiling with gravitational interactions. You'd expect a galaxy embedded in this cosmological maelstrom to experience frequent mergers, interactions, or at least some form of harassment from neighboring galaxies. Yet, NGC 1277 has avoided this fate. One hypothesis suggests that NGC 1277's orbit within the cluster is highly circular and fast-moving, allowing it to avoid spending too much time in the denser, central regions of the cluster where mergers are more common. Like a lone wolf sprinting along the periphery of a battlefield, it moves just quickly enough and just distantly enough to avoid being caught in the crossfire. This orbital behavior could be the very reason it has remained a relic. It has managed, quite literally, to outrun change. Now imagine this galaxy not as an inert lump of ancient stars, but as a frozen wave, a fossilized burst of ancient motion that never fully decayed. The kinetic energy within it, the orbital angular momentum, the memory of its formation, all preserved in a cocoon of time. Every star within it still sings the tune of that long-past formation epoch, a song composed in fire and gravity and silence too soon. There is a poetic symmetry in how the light from these stars travels billions of years through the cosmos, only to be captured by our instruments. Each photon carries with it a story, of birth, of compression, of violent ignition followed by a darkening hush. Every data point, every spectral line, every redshift value is a footnote in this galactic eulogy. In studying NGC 1277, we are not just analyzing a collection of matter. We are peering into a preserved narrative from a time when the universe was still assembling its lexicon of form and chaos. What makes this even more profound is the black hole's role in this narrative. At roughly 17 billion solar masses, give or take, this black hole defies nearly every scaling relation we've established. Galaxies of this size should not host such a massive central object. This leads to an even deeper question: what if we've misunderstood black holes entirely? What if black holes don't merely evolve alongside galaxies, but sometimes dominate their evolution, even halting it? The feedback from such a massive object could have shut down star formation early on by blasting out gas with powerful winds and radiation. We often think of feedback as a delicate balancing act, enough to regulate, not enough to extinguish. But NGC 1277 suggests the possibility of overkill, of galactic sterilization on a grand scale. One colossal feedback event from this black hole, and the future of star formation in the entire galaxy could have been obliterated. And then there's the question of time. In astronomy, time is not a passive backdrop. It is an active, shaping force. The age of a star, the age of a galaxy, the time since the last collision, all of these are dynamic variables that influence everything from structure to color to spectral output. NGC 1277 is a masterclass in astronomical time. Its stars are ancient, and their age defines everything about the galaxy, from its red hue to its dead silence in the X-ray spectrum. If you were to compress the history of the universe into a single year, with the Big Bang occurring at midnight on January 1st and the present moment ticking in at the final second of December 31st, then NGC 1277's formation happened in the first cosmic month, early February, when the universe was just figuring out how to cool down and coalesce. That is the era NGC 1277 remembers. Everything since then, supernovae, black hole mergers, the growth of our own Milky Way, has played out in the silence of its distant observation. In its silence, NGC 1277 echoes the deepest truths of the cosmos, that not all things grow, not all paths evolve. Some simply are. Now let us visualize what it would mean to travel there. Not as observers from Earth, but as explorers drifting through the intergalactic void, slowly approaching this dark giant. The journey itself would be unimaginable in human terms, measured not in years, but in lifetimes of civilizations. As we draw closer, we pass through the Perseus cluster, navigating a sea of X-ray emitting gas heated to tens of millions of degrees. The cluster's core looms ahead, a jungle of gravitational tides and infalling matter. But NGC 1277 remains aloof, spinning quietly at the outskirts. As we reach the galaxy, we pass into its stellar halo, sparse and ancient. The stars here are metalpoor, survivors of the earliest stellar generations. The light around us turns redder, dimmer, until we pass into the galaxy proper, a region where every cubic light-year teems with ancient suns. There are no brilliant blue stars here, no great nebulae. The landscape is quiet, haunted, and beautiful. Moving toward the center, the stellar density increases dramatically. We pass through globular clusters, some perhaps older than our own solar system, orbiting the galaxy like relic satellites. Then comes the gravitational deep end, stars moving at incredible velocities, twisting around the core like leaves in a whirlwind. Here, relativistic effects begin to dominate. Time dilates. Light bends. We are now in the kingdom of the black hole. The gravitational well of this black hole would stretch and twist spacetime itself. If we could hover near its event horizon, we would see the rest of the universe blue shift into a brilliant point, while time for us slows to a crawl. It would be the ultimate laboratory for Einstein's theories, and perhaps for the ones that must come after. And yet, despite its terrifying power, this black hole is silent. No jets. No flares. Just an invisible sphere of infinite density, and eternal hunger. This silence is not emptiness. It is fullness. It is the silence of something that has consumed and ended, that has no more need to rage or announce itself. It is the silence of the ancient, of the completed. But is NGC 1277 truly finished? There is always the possibility, however remote, that some new event will awaken it. A rogue gas cloud. A stray dwarf galaxy. A dark matter filament that twitches and pulls. Even in the most static of systems, change is never entirely ruled out. And when you are a galaxy billions of years old, even the most improbable events have time to occur. Until then, NGC 1277 remains as it is, a relic, a time capsule, a cosmic anomaly. It watches without eyes. It waits without desire. It spins not because it must, but because it always has. And in doing so, it continues to remind us that the universe is not merely what we can explain, but also what we have yet to imagine. Let us now drift even deeper into the story of NGC 1277, a galaxy whose silence has become its loudest feature in the cosmos. A galaxy so enigmatically unchanged that it bends not only the rules of galactic evolution, but also the expectations we hold about the life cycle of the universe itself. It remains a cosmic fossil, a galactic tomb that whispers secrets of a bygone era in every spectrum of light it reflects. But to truly understand the implications of NGC 1277's existence, we must go far beyond its physical structure and into the surrounding framework of cosmology, gravitational theory, intergalactic dynamics, and even the philosophical consequences of observing something so ancient and so unchanging. Imagine for a moment if we could tap into the memory of the universe itself, a memory stored not in thoughts, but in motion, light, radiation, and gravity. NGC 1277 would be one of the first memories, frozen in time, almost as though the universe itself bookmarked this location for reasons we've yet to uncover. We're staring at a galaxy that formed most of its stars during the first few billion years after the Big Bang and then, inexplicably, stopped. It refused to grow. It refused to merge. It refused to ignite with the chaotic energy that shaped its galactic cousins. Instead, it fossilized in place, and with that became a living paradox in the expanding universe. We've already touched upon the possibility that its central black hole may have sterilized the entire galaxy early in its life. But let us now explore what that truly means in the broader context of astrophysical feedback mechanisms. Normally, galaxies experience something called AGN feedback, an active galactic nucleus phenomenon, where the central black hole radiates enough energy to influence star formation. This process can either stimulate or quench star formation depending on the energy output and the available gas supply. But in NGC 1277, the feedback wasn't just strong, it was final. It was as if the galaxy declared the end of its own development after an early, violent episode of energy release from the black hole, like a painter finishing a masterpiece in the first few brushstrokes, and then walking away forever. There's a name for galaxies like this: relic galaxies. They are the untouched survivors of a more violent, formative cosmic era. But NGC 1277 is not just any relic galaxy. It is the archetype, the alpha, the purest example we've discovered so far. Its stars are older than 10 billion years. It contains little to no cold gas. It shows no signs of recent star formation. It is as if the cosmic clock for this galaxy stopped ticking just after it began. And in a universe that has since erupted with color, light, and growth, this galaxy has become an anomaly of stillness. Now think about the galactic neighborhood it resides in, the Perseus cluster. This is not a quiet region of space. This cluster is a gravitational cauldron, filled with high-speed galaxy interactions, X-ray emitting gas, and a chaotic ballet of matter and energy. It's the last place you'd expect to find a galaxy that seems to have never been touched. It's like discovering a fully intact vase buried beneath a battlefield. And yet there it is. Why didn't it get swept into the gravitational chaos? One idea posits that it orbits the cluster in such a way, at such velocity and distance, that it avoids the dense inner regions where interactions are more likely. In this way, NGC 1277 becomes a cosmic ninja, stealthily evading encounters that might disturb its pristine form. That doesn't mean it hasn't been affected at all. Even the most isolated galaxies and clusters feel tidal forces, gravitational lensing, and cosmic background radiation. But NGC 1277 has somehow remained structurally unaltered, a feat akin to a city untouched by time, weather, or war. Its mass distribution further cements its bizarre status. Galaxies with such compact structures, extremely high central density with little extended halo, are almost non-existent in the current era. Yet NGC 1277 defies this norm. It has a huge concentration of stars within a relatively small volume, giving it one of the highest stellar velocity dispersions ever measured. This makes it a prime laboratory for testing the limits of gravitational physics. When we model galaxies, we rely on certain scaling relations, like the m-sigma relation, which links the mass of a central black hole to the velocity dispersion of stars in the galaxy. NGC 1277 doesn't just break this relationship, it annihilates it. Its black hole is far too massive for a galaxy of its size. In fact, its black hole represents about 14% of the total mass of the galaxy's stellar content. For context, in our Milky Way, the central black hole makes up only about 0.01% of the total stellar mass. This is not just unusual, it's unprecedented. It throws a wrench into our understanding of how galaxies and black holes co-evolve. We once believed that black holes grew in step with their host galaxies, in a kind of cosmic dance where both partners fed off the same pool of material. But NGC 1277 may suggest a different narrative, that some black holes can outgrow their galaxies, becoming the dominant structure, the heart that swells beyond what the body can support. There's a dark poetic irony here. We think of black holes as invisible, as holes in the fabric of space-time. But in NGC 1277, the black hole is the most significant feature. The hole is the anchor. The hole is the identity. The galaxy is merely its ornament. If the stars were to somehow dissolve, the black hole would remain, floating through the cluster, carrying with it the remnants of a once pristine relic. And if we let our imaginations wander further, into the realm of cosmic speculation, one must ask, are there more of these relics? Are there galaxies like NGC 1277 hiding in other clusters, invisible to our instruments, waiting to be discovered? If NGC 1277 survived the chaotic adolescence of the universe, perhaps others did too. They could be lurking in the gravitational outskirts of clusters, shielded by high-velocity orbits, their light too dim or redshifted for our current telescopes to detect. These would be not just relic galaxies, but relic black holes, ancient engines of entropy that hold the memory of the universe's youth. Even more tantalizing is the possibility that such relic galaxies might host clues to the conditions of the early universe that we can't access any other way. Unlike quasars, which burn brightly and change rapidly, relic galaxies are quiet archives. Every star, every globular cluster, every dark matter halo, and every orbital velocity in NGC 1277 is a page in the cosmic history book, written in gravitational ink. Now zoom out in your mind. Picture the observable universe, trillions of galaxies, each with its own history, structure, chaos, and balance. Among this incomprehensible ocean of matter and energy, one galaxy stands still, like an island of order in a sea of entropy. That is NGC 1277. What it tells us is not only that galaxies can evolve in unexpected ways, but that our models, our cherished equations and scaling laws, may be oversimplified. It humbles us. It reminds us that for all our simulations and surveys, the universe still harbors ghosts from a time when physics itself was still learning how to write. Let's now pull even closer to the gravity of the enigma, the heart of the beast itself, the supermassive black hole within NGC 1277. Its mass, measured to be over 17 billion times that of our Sun, is so colossal that it challenges the very definitions we use for black holes. Traditionally, we thought black holes of this magnitude could only be found at the centers of extremely massive galaxies, the types with sprawling spiral arms or huge elliptical halos, sometimes containing hundreds of billions of stars. But NGC 1277 defies that. It's a compact lenticular galaxy, not much bigger than the Milky Way, and yet it hosts a black hole far larger than the one in the center of our own. This discovery didn't just shock astronomers. It rattled cosmological theory. Because it isn't just that the black hole is big, it's too big. If you chart it on the standard black hole scaling laws, it lies far off the curve, suggesting either that NGC 1277's black hole grew far too quickly in the early universe, or that it was formed under a different set of cosmic conditions altogether. Either option presents fascinating implications. If it grew quickly, it challenges our assumptions about how much material could have been available in the early epochs. If it formed differently, then we may be looking at a fundamentally different type of object, a primordial black hole, or perhaps even the remnant of a small early galactic cluster that collapsed catastrophically. And the very presence of such an ancient and overweight black hole suggests a dark possibility that NGC 1277 might not be an isolated relic, but the survivor of some ancient cosmic culling. There is a haunting theory that galaxies like NGC 1277 once lived in a much more crowded environment, a protocluster teeming with other proto-galaxies, and through a series of rapid mergers, high-energy interactions, and gravitational cannibalism, a few dense cores like NGC 1277 survived the carnage, while everything else was shredded, absorbed, or flung into intergalactic space. If that's true, then NGC 1277 might not just be a fossil, it might be the last standing monument of a destroyed city of galaxies. But let's focus on that black hole's behavior. Is it active? Does it consume matter, emit radiation, generate jets? Strangely, no. Not anymore. It's quiet now, eerily quiet. This suggests that the black hole in NGC 1277, like the galaxy around it, has entered a deep slumber. It has already devoured whatever matter it once had access to. The accretion disk that may have once burned with high-energy X-rays has long since faded. It sits in gravitational silence, like a monarch who has conquered all territory and now rules over emptiness. This is key to understanding why NGC 1277 hasn't formed new stars in billions of years. Its interstellar medium was likely stripped or heated beyond use long ago, leaving behind a stellar graveyard and a black hole ruler. And that stellar population, it's just as intriguing. Spectroscopic analysis reveals that NGC 1277 stars are not just old, they're ancient, with the majority having formed more than 10 billion years ago. There's a sharp lack of metal-rich young stars, which typically result from more recent star formation. Instead, the stellar population is uniform, metal-poor, and dynamically relaxed, more evidence that the galaxy hasn't undergone mergers or major gas inflows in eons. The stars rotate rapidly around the central bulge, indicating a dense, rotationally supported system that has remained dynamically coherent for nearly the entire age of the universe. In many ways, NGC 1277 is the Rosetta Stone of early galaxy formation. Because it hasn't changed much since its birth, it acts as a reference point, a preserved example of what some of the universe's first galaxies might have looked like. This is why it is studied obsessively with every telescope capable of peering into its structure, from Hubble to Keck Elme. It offers insight not just into one galaxy's history, but into a critical phase of the cosmos that we rarely get to see unaltered. Now consider the broader implications. If NGC 1277 is a relic galaxy, and we accept that such galaxies are rare survivors of early cosmic history, then every property it has can be used as a cosmic measuring stick. Its black hole mass, its stellar rotation curve, its metallicity, its surface brightness profile, all of these help refine our models of early galaxy formation. And when those models fail to accommodate what we observe, we are forced to rewrite the physics. We have to consider new initial conditions, more aggressive feedback mechanisms, and radically different merger histories. In this way, NGC 1277 is not just rewriting its own story, it's rewriting the story of galaxy evolution. But let us stretch our imagination even further, into the realm of galactic archaeology. Think of the Milky Way as a bustling city, with constant construction, renovation, and expansion. Now picture NGC 1277 as a sealed tomb, untouched for billions of years, its secrets entombed in gravitational silence. What would we find if we could enter its inner sanctum? What if the globular clusters orbiting its periphery are ancient satellites, each one a microgalaxy that was captured during the galaxy's chaotic birth? What if we find dark matter distributions that don't match modern expectations, indicating that the nature of dark matter itself may have changed over cosmic time? Some researchers have even speculated that galaxies like NGC 1277 might house exotic objects not yet observed elsewhere, long-lived supermassive stars, collapsed primordial objects, or even stable configurations of dark matter that couldn't form under current universal conditions. It's a speculative frontier, yes, but so was the idea of supermassive black holes itself, just a few decades ago. There is something profoundly humbling about such a galaxy. It doesn't just sit in the Perseus cluster like a data point. It challenges us. It holds a mirror up to our theories and shows us their cracks. It asks questions in silence. It teaches by simply existing. In the growing field of observational cosmology, where data pours in faster than theory can keep up, NGC 1277 reminds us that not all discoveries come from new technology. Some come from finding the right thing to observe, and asking the right questions about why it looks the way it does. The greatest mystery of NGC 1277 might not be what it is, but why it stopped becoming. In a universe where galaxies fight, grow, merge, and evolve, NGC 1277 simply opted out. It declared an end to its own change. That might make it the most alien object we've ever observed, not because it defies physics, but because it chose, somehow, to stop playing by the same rules. And so, NGC 1277 spins, fast, quiet, old. Surrounded by younger, more chaotic neighbors. Guarded by a black hole too large to ignore. An ancient library in the heart of the Perseus cluster. Waiting, watching, unchanged. NGC 1277's story, however, does not exist in isolation. It resides within the Perseus cluster, one of the most massive galaxy clusters known, a cosmic metropolis teeming with activity and collisions, where galaxies interact, collide, and sometimes cannibalize each other in a chaotic dance over billions of years. The environment surrounding NGC 1277 offers crucial clues to understanding how this galaxy managed to preserve its relic status despite the tumultuous neighborhood it inhabits. Galaxy clusters like Perseus are dense, gravitationally bound collections of hundreds to thousands of galaxies embedded in vast clouds of hot, X-ray emitting gas. This intra-cluster medium bathes galaxies as they plunge through it, stripping them of gas and quenching their star formation, a process known as ram pressure stripping. This cosmic mechanism may have played a critical role in freezing NGC 1277's development. As the galaxy fell into the Perseus cluster early in its life, it likely lost its cold gas reservoirs, essential for new star formation, effectively sealing its fate as a red and dead galaxy. This premature cessation of star birth is a hallmark of many cluster galaxies, but is especially poignant for NGC 1277 due to its compact size and dense stellar population. The cluster environment also intensifies gravitational interactions. Galaxies gravitationally tug and twist one another, distorting shapes and occasionally merging to create larger galaxies. NGC 1277's survival as a compact, undisturbed entity suggests it either avoided direct collisions or withstood them without losing its unique structure. This resilience points toward an early, rapid formation period, after which it became an isolated survivor amid the cosmic chaos. One must consider the dynamical history of NGC 1277 to understand how it avoided significant mergers. Its high stellar velocity dispersion and rapid rotation support the idea that it is a fast rotator, a galaxy type that can resist disruption by maintaining angular momentum. This preservation of angular momentum is rare in dense cluster environments, where chaotic interactions tend to scramble stellar orbits, transforming galaxies into slow rotators or ellipticals. Moreover, the dense stellar core of NGC 1277 provides insights into star formation under extreme conditions. The core is unusually compact and massive, implying that its stars formed rapidly in a brief, intense burst of star formation, a cosmic firestorm, within the first billion years of the universe's history. This rapid star formation produced a dense spheroid of old stars that would later shield the galaxy from environmental effects, making it a fossil of early cosmic epochs. The monster black hole at NGC 1277's center, constituting approximately 14% of the galaxy's total stellar mass, is an unprecedented fraction compared to typical galaxies where the black hole mass is usually less than 0.5% of the stellar mass. This disparity raises profound questions about black hole galaxy coevolution. Did the black hole's growth regulate the galaxy's star formation by heating or expelling gas through energetic feedback processes? Or did the black hole's mass accumulation precede and perhaps even cause the galaxy's quenching? Astronomers speculate that powerful outflows from the black hole, via jets or radiation pressure during active phases, may have swept away or heated the interstellar gas, preventing further star formation. This scenario aligns with feedback models crucial in contemporary galaxy evolution theory, where black holes act as regulators of galactic growth, halting star formation by controlling the gas supply. NGC 1277's inactive current state suggests the black hole's active feeding phase occurred early on, and was followed by a prolonged quiescent period. However, this black hole could reignite if it encounters fresh material, potentially transforming the galaxy's environment dramatically. Monitoring NGC 1277 across the electromagnetic spectrum could reveal signs of such activity, offering a rare opportunity to witness the interplay between black hole feeding and galaxy evolution in real time. Furthermore, NGC 1277 challenges the simplistic classification of galaxies by blurring the lines between normal galaxies and extreme outliers. It invites us to reconsider the diversity of galactic evolution pathways and to appreciate that our cosmic neighborhood harbors relics that defy typical scaling relations and evolutionary models. Exploring NGC 1277 also connects us to broader questions in cosmology and black hole physics. Its enormous black hole serves as a natural laboratory for studying supermassive black hole formation mechanisms. Did such massive black holes form from the direct collapse of primordial gas clouds, bypassing the traditional stellar mass black hole growth stages? Or were they born from the mergers of smaller black holes, growing through repeated accretion over cosmic time? Understanding these processes has ripple effects on theories about early universe structure formation, the reionization epoch, and even gravitational wave sources detectable by future observatories. NGC 1277's status as a relic galaxy powered by a monster black hole encapsulates the dual nature of cosmic history: preservation amid change, silence amid violence, and mystery amid knowledge. It stands as a testament to the complex interplay of forces shaping galaxies, offering a window into the universe's formative years and a challenge to our understanding of cosmic evolution. Delving deeper into the nature of NGC 1277, it becomes essential to explore the intricate details of its stellar population, the chemical makeup of its stars, and how these factors contribute to our understanding of its origin and evolution. The stars in NGC 1277 are predominantly old and metal-rich. In astrophysical terms, metals refer to elements heavier than hydrogen and helium, forged inside stars and distributed into the interstellar medium through supernova explosions. The abundance of these metals in NGC 1277 stars suggests that the galaxy underwent rapid and efficient star formation early in its life, enriching its environment quickly before shutting down further star birth. Spectroscopic studies of NGC 1277 stellar light reveal signatures indicative of an intense burst of star formation lasting less than a billion years, followed by a sudden truncation. This swift timeline is consistent with the concept of a red nugget, a class of compact, massive galaxies identified at high redshifts, which are believed to be the building blocks of larger galaxies in the modern universe. However, unlike typical red nuggets that eventually grow through mergers and interactions, NGC 1277 has remained relatively unchanged, preserving its compact form and stellar content. Its compactness is astonishing. The galaxy's half-light radius, The radius within which half its total light is emitted is only about 1,600 light-years, which is tiny compared to the Milky Way's half-light radius of roughly 16,000 light-years. Despite this, NGC 1277 packs a stellar mass of approximately 1.2 times 10 to the power of 11 solar masses, meaning it crams a mass equivalent to a large spiral galaxy into a volume roughly 10 times smaller. This extreme density makes NGC 1277 one of the densest known galaxies in the nearby universe. The structural features of NGC 1277 provide clues about its internal dynamics and formation. It displays a high degree of rotational support, meaning stars orbit the galaxy's center in a coherent manner rather than moving randomly. This ordered motion contrasts with the chaotic stellar orbits seen in elliptical galaxies formed by multiple mergers. Such rotational characteristics suggest that NGC 1277 formed through a rapid collapse of gas that conserved angular momentum, forming a dense, spinning disk or spheroid early in the universe's history. NGC 1277's environment further influences its current state. Located near the center of the Perseus cluster, it is surrounded by hot, X-ray emitting gas that permeates the cluster space. This intracluster medium plays a vital role in suppressing gas accretion onto galaxies like NGC 1277, preventing fresh fuel from reigniting star formation. Additionally, gravitational interactions with neighboring galaxies and the cluster's tidal forces can strip gas and stars from galaxies or distort their structures. Yet, NGC 1277's compactness and dense core have likely shielded it from significant disruption, allowing it to retain its distinct identity amidst the cluster's chaos. Turning back to the colossal black hole at its center, the details surrounding its discovery and measurement are fascinating. Early studies using the Hubble telescope revealed unusually high stellar velocities near the core, suggesting the presence of an extremely massive object. Subsequent detailed dynamical modeling confirmed a black hole mass on the order of 17 billion solar masses, dwarfing the Milky Way's central black hole by nearly 4,000 times. This extreme mass ratio challenges the well-established scaling relations that link black hole mass to the properties of the host galaxy's bulge, such as stellar mass or velocity dispersion. These scaling relations have been pivotal in understanding the coevolution of black holes and galaxies, implying a symbiotic growth regulated by feedback mechanisms. NGC 1277's deviation from these trends suggests alternative growth pathways or that it represents a frozen snapshot of black hole and galaxy formation from the early universe, before such relationships were firmly established. It raises profound questions about whether black holes in the early universe could have grown independently or faster than their host galaxies, hinting at a more complex and varied cosmic evolution than previously thought. The enormous gravitational influence of NGC 1277's black hole extends beyond just the immediate galactic center. It shapes the dynamics of the surrounding stars, causing high-velocity dispersions and influencing orbital patterns. This black hole's sphere of influence is vast, dominating the gravitational potential well of the galaxy and possibly affecting the retention of gas and dark matter within the galaxy's core. Recent advances in observational astronomy, including adaptive optics and integral field spectroscopy, have allowed astronomers to map the stellar motions in exquisite detail, revealing how the stars respond to the black hole's gravitational pull. These data are crucial in refining mass estimates and understanding the interaction between the black hole and its stellar environment. The origin of such a monster black hole remains an open and intriguing question. Two main theories contend to explain its formation. One posits that the black hole grew via rapid accretion of gas and merging with other black holes in the dense early universe, a process known as hierarchical growth. Alternatively, the black hole could be a remnant of a primordial massive seed formed through direct collapse of massive gas clouds in the early cosmos, bypassing smaller mass stages. This latter scenario aligns with observations of supermassive black holes at high redshifts that appear too massive to have grown solely through accretion within the available time since the Big Bang. Understanding NGC 1277's black hole also informs research into gravitational waves. mergers of supermassive black holes are expected to produce powerful gravitational waves detectable by future space-based observatories. Studying galaxies like NGC 1277 provides insight into how such black hole mergers might occur, and their frequency in galaxy clusters. Moreover, NGC 1277 challenges astronomers to refine galaxy formation simulations. Numerical models must account for its compactness, stellar population, black hole mass, and environment simultaneously, demanding a multi-scale approach to cosmic structure formation. These simulations are vital for testing hypotheses about early galaxy assembly, and the role of feedback in shaping the diverse galaxy population we observe today. NGC 1277 serves as a cosmic Rosetta Stone, translating the complex language of galaxy and black hole coevolution. Its relic status and extreme black hole challenge conventional wisdom and open new avenues for exploring the formative epochs of the universe, the behavior of matter under intense gravity, and the cosmic history recorded in the stars. The story of NGC 1277 does not end with its structural properties or the gargantuan black hole alone. To truly appreciate this galaxy, we must immerse ourselves in the broader context of cosmic evolution, examining how galaxies interact, evolve, and sometimes, like NGC 1277, defy expectations by remaining essentially frozen in time. Galaxies are dynamic entities, constantly shaped by their surroundings. Most massive galaxies in the universe today have grown through a combination of star formation fueled by gas inflows and mergers with smaller galaxies. This hierarchical buildup tends to alter their shapes, sizes, and stellar populations. Over billions of years, galaxies like the Milky Way have accreted smaller satellites, reshaped their disks, and experienced bursts of star formation triggered by gravitational interactions. Yet, NGC 1277 stands as an exception, a galaxy that appears to have undergone rapid, early growth, then remained remarkably stable for over 10 billion years. This relic-like quality offers astronomers a rare laboratory to study conditions akin to the universe's infancy. By comparing NGC 1277 to galaxies at high redshift, researchers gain insight into the processes that govern the early cosmos. Its stellar population, composed mainly of old, metal-rich stars, aligns well with the characteristics of red nuggets observed in the early universe, supporting the idea that it is a local counterpart of these primordial galaxies. One intriguing aspect of NGC 1277 is its apparent lack of significant gas and dust, the raw materials for star formation. Observations across multiple wavelengths show that it is largely devoid of the cool gas clouds that power new star birth in many other galaxies. This gas depletion hints at past energetic events that may have expelled or heated the gas, preventing further star formation. Such events could include powerful outflows driven by the central black hole, a process known as active galactic nucleus (AGN) feedback, or supernova explosions during the galaxy's intense starburst phase. AGN feedback, in particular, plays a crucial role in regulating galaxy growth. When a supermassive black hole actively accretes matter, it can release enormous amounts of energy, heating or ejecting gas from the galaxy's core and halting star formation. In NGC 1277, it is possible that the monster black hole's past activity effectively shut down the galaxy's star formation, locking it into a passive evolutionary state. The black hole's mass and influence thus not only mark it as an astrophysical giant, but also as a cosmic regulator, dictating the galaxy's fate. Another layer of complexity arises from NGC 1277's dark matter content. Dark matter, the mysterious and invisible substance that dominates the universe's mass budget, forms the gravitational scaffolding around which galaxies assemble. While NGC 1277's stellar mass and black hole dominate the central regions, understanding its dark matter halo is critical to comprehending its overall mass distribution and evolutionary path. Studies indicate that NGC 1277 may have an unusually low dark matter fraction within its inner regions compared to typical galaxies. This suggests that the galaxy's compact stellar mass may dominate its gravitational potential in the core, making it an extraordinary case study for disentangling the roles of baryonic, normal, matter and dark matter in galaxy formation. This peculiarity also challenges models of how dark matter halos interact with baryonic processes, offering clues to the interplay between visible and invisible components of the cosmos. Furthermore, NGC 1277's position within the Perseus cluster shapes its destiny. The cluster environment subjects galaxies to intense gravitational interactions, high-velocity encounters, and a hot, dense intracluster medium. These forces can strip galaxies of their gas through processes like ram pressure stripping, strangulation, or tidal interactions, effectively quenching star formation and altering morphologies. Yet, despite residing in such a tumultuous neighborhood, NGC 1277's compact structure and dense core have likely helped it resist significant disruption. It stands as a cosmic survivor, its relic nature preserved by both internal dynamics and external circumstances. This resilience provides an extraordinary example of how environmental effects can vary, highlighting the delicate balance of forces that shape galaxy evolution. Moving beyond the galaxy itself, the enormous black hole at its center holds profound implications for astrophysics and cosmology. The black hole's mass, measured to be about 17 billion times that of our Sun, places it among the heaviest known supermassive black holes. Such a monstrous mass raises pressing questions about black hole formation mechanisms, growth rates, and the limits imposed by physics. In particular, the presence of such a supermassive black hole in a relatively small galaxy defies the conventional correlation between black hole mass and galaxy properties. This discrepancy challenges our understanding of black hole-galaxy coevolution and suggests that black holes might sometimes grow independently or ahead of their hosts. The processes enabling such rapid black hole growth could include direct collapse of massive gas clouds in the early universe or rapid accretion during gas-rich phases, followed by a shutdown of galaxy growth. The study of NGC 1277 thus provides critical data for refining theoretical models of black hole evolution. It emphasizes the need for incorporating diverse pathways in simulations, recognizing that not all galaxies and black holes follow a uniform evolutionary track. By probing the extremes, astronomers gain insight into the fundamental physics governing gravity, matter, and energy under extreme conditions. Moreover, NGC 1277's black hole is a potential key to understanding gravitational waves emitted by supermassive black hole mergers. When galaxies collide, their central black holes may eventually coalesce, producing ripples in spacetime detectable by future observatories like the Laser Interferometer Space Antenna, LISA. Studying galaxies with massive black holes enhances predictions about merger rates, gravitational wave signals, and the cosmic history of black hole interactions. The galaxy's enigmatic qualities also provoke philosophical contemplation about our cosmic origins and fate. As a relic galaxy, NGC 1277 is a time capsule, preserving the conditions of an era when the universe was young and dynamic. It reminds us that the cosmos is a tapestry woven from both grand transformations and remarkable stasis, where some systems evolve rapidly and others remain frozen across billions of years. In this light, NGC 1277 exemplifies the universe's complexity and diversity, highlighting the interplay between cosmic forces that create order, chaos, growth, and preservation. It invites ongoing exploration, challenging scientists to uncover the mysteries embedded in starlight, gravity, and time itself. NGC 1277's story extends even deeper into the realm of stellar dynamics and chemical composition, providing astronomers with a rich field of data to decode. The stars within this galaxy are remarkably old, estimated to be about 12 billion years in age, which places their formation close to the dawn of the universe itself. The ages of these stars are determined by analyzing their spectra, essentially the light fingerprints emitted by the galaxy, allowing scientists to gauge the chemical abundances and infer the timeline of star formation. The stars in NGC 1277 exhibit high metallicity, meaning they contain a relatively large proportion of elements heavier than hydrogen and helium. This high metallicity suggests a rapid and intense period of star formation early in the galaxy's history, where successive generations of stars synthesized heavy elements through nuclear fusion and supernova explosions. Such enrichment points to a burst of stellar creation that likely consumed the galaxy's available gas quickly, leaving little fuel for continued star formation in later epochs. Moreover, the internal kinematics of NGC 1277, the motions of its stars and gas, reveal fascinating details about its formation and evolution. Measurements show that the galaxy has a fast-rotating disk component, unusual for elliptical galaxies, which are often dominated by random stellar motions. This fast rotation hints at a formation scenario involving dissipative collapse, where gas settled into a disk before forming stars, rather than the galaxy being built solely through chaotic mergers. This disk-like rotation contrasts with many massive galaxies that are typically slow rotators, reinforcing NGC 1277's unique character. The central black hole's gravitational influence significantly shapes the dynamics of stars near the core. Stars orbit at tremendous speeds around this gravitational behemoth, their paths governed by its immense pull. Observing these stellar velocities helps astronomers estimate the black hole's mass and understand the distribution of matter in the galaxy's heart. The precise measurement of stellar orbits near the black hole serves as a direct probe of gravitational physics in extreme regimes, providing tests for Einstein's theory of general relativity and potential windows into new physics. Beyond the immediate stellar and black hole environment, NGC 1277 resides within the Perseus cluster, one of the most massive known galaxy clusters located approximately 250 million light-years away. This dense cluster environment is filled with hot ionized gas-emitting X-rays, which bathes the galaxies in intense radiation and subjects them to complex interactions. Such harsh surroundings influence galaxy evolution through mechanisms like galaxy harassment, where repeated high-speed encounters strip away gas and stars, or ram pressure stripping, where the intracluster medium sweeps away a galaxy's gas content. Yet, NGC 1277's compact size and dense stellar population suggest it has resisted these environmental forces more effectively than many other cluster members. Its survival intact amidst the tumultuous cluster environment adds to the intrigue, positioning it as a robust relic that defies the destructive tendencies common in such regions. Theoretical modeling of NGC 1277's formation also highlights the role of early cosmic conditions. The galaxy likely formed in a dense primordial region with a high concentration of cold gas, facilitating rapid star formation and black hole growth. Its early assembly may have been followed by a quenching event, potentially driven by the black hole's energetic feedback, that halted gas accretion and star formation, effectively locking the galaxy into a passive evolutionary phase. This quenching process not only prevented further stellar births but also influenced the structural properties of NGC 1277. Without fresh gas inflows to fuel star formation or mergers to disrupt its shape, the galaxy preserved its compactness and stellar distribution over cosmic time. This makes it a rare example of a so-called red nugget. Compact, massive, and old galaxies originally common in the early universe but now exceedingly rare. The discovery and study of galaxies like NGC 1277 have profound implications for our broader understanding of galaxy evolution. They challenge traditional models that assume steady growth through mergers and gradual star formation decline. Instead, these relic galaxies point to alternative pathways where rapid early assembly and abrupt quenching produce compact, massive systems that endure largely unchanged for billions of years. Additionally, NGC 1277's overmassive black hole forces a re-examination of the empirical relationships between black hole mass and host galaxy properties, such as bulge mass and velocity dispersion. These relationships underpin much of modern astrophysics, used to infer black hole masses across the universe and understand galaxy-black hole coevolution. Exceptions like NGC 1277 suggest that these correlations may not be universal, especially in extreme or early universe environments. Such discoveries motivate astronomers to refine observational techniques and develop new theoretical frameworks to encompass a wider diversity of galactic phenomena. They underscore the complexity of cosmic evolution and the many unanswered questions about how galaxies and black holes grow and interact. Looking ahead, future observations with next-generation telescopes, such as the James Webb Space Telescope, JWST, and extremely large ground-based observatories, promise to unlock even deeper insights into NGC 1277 and similar relic galaxies. These instruments will enable detailed studies of their stellar populations, black hole environments, and chemical histories at unprecedented resolution and sensitivity. Moreover, the study of gravitational waves from black hole mergers, facilitated by detectors like LISA, will complement electromagnetic observations by revealing the merger histories of massive black holes, providing clues about their growth and the dynamics of host galaxies. NGC 1277 stands as a cosmic puzzle piece, connecting us to the earliest epochs of galaxy formation, the extremes of black hole physics, and the complex interplay of forces shaping the universe. Its study exemplifies the power of modern astronomy to probe fundamental questions about our cosmic origins and the mechanisms governing the evolution of the grandest structures in the cosmos. In this grand narrative, NGC 1277 is not just a distant, compact galaxy. It is a testament to the universe's diversity, a relic survivor from the cosmic dawn, and a beacon guiding our quest to unravel the mysteries of space, time, and gravity. Let's delve even deeper into the fascinating enigma that is NGC 1277, exploring its place not just as an isolated relic but as a fundamental piece in the cosmic puzzle of galaxy and black hole evolution. The extraordinary mass of the black hole at NGC 1277 center raises questions about the mechanisms that could lead to such an overgrowth. One leading hypothesis involves the concept of direct collapse, black holes in the early universe. In this scenario, massive black hole seeds formed rapidly from the collapse of pristine gas clouds without first becoming stars. This process would allow black holes to attain supermassive scales far earlier than traditional models predict. If NGC 1277's black hole originated from such a seed, it could explain how it grew so massive so quickly, well before the galaxy had time to form an extensive stellar population. Alternatively, frequent and rapid accretion events, where gas funnels into the black hole, feeding it at rates near or above the Eddington limit, could have contributed to this monster black hole's growth. The intense gravitational pull of the black hole would have drawn in surrounding matter, releasing vast amounts of energy and potentially impacting star formation in the galaxy by heating or expelling gas, thereby suppressing further stellar births. This feedback loop, where the black hole's energy output regulates the galaxy's gas content, is a cornerstone of modern galaxy evolution theory. In the case of NGC 1277, it may have been particularly efficient, halting star formation early and cementing the galaxy's compact, red nugget, structure. Exploring NGC 1277's environment within the Perseus cluster adds yet another dimension to understanding its evolution. Galaxy clusters are dynamic ecosystems where gravitational interactions and the hot intracluster medium shape the fate of member galaxies. For instance, tidal forces from close encounters can strip gas and stars, transforming galaxies over time. Yet, NGC 1277's survival intact suggests it might have been shielded in some way, perhaps by residing in a subcluster or having a more stable orbit within the cluster potential well. The hot intracluster medium, composed of ionized plasma-emitting X-rays, also plays a critical role. This medium can strip gas from galaxies traveling through it at high speeds via ram pressure stripping, depriving them of the raw material needed for star formation. NGC 1277's apparent gas-poor nature fits this picture, consistent with a galaxy that has long been quiescent. Comparing NGC 1277 to other red nuggets provides further insight into early galaxy evolution. These compact, massive galaxies are thought to be the cores of larger galaxies that failed to undergo significant mergers or growth. While many red nuggets have since merged and grown into giant elliptical galaxies, NGC 1277 remains a pristine example, frozen in cosmic time. Studying such relics helps astronomers reconstruct the conditions of the early universe, offering snapshots of galaxy formation in its initial stages. From a chemical perspective, the detailed abundance patterns in NGC 1277 stars reveal clues about the initial mass function, IMF, the distribution of stellar masses formed during star formation episodes. Some studies suggest that the IMF and massive relic galaxies may be bottom-heavy, meaning a higher proportion of low-mass stars formed compared to typical galaxies. This unusual IMF would influence the galaxy's mass-to-light ratio and stellar dynamics, impacting measurements of both stellar and dark matter content. Dark matter, the invisible yet dominant component of cosmic matter, also factors into understanding NGC 1277. Its role in forming the galaxy's gravitational potential well is crucial, but disentangling the contributions of dark matter from stars and the central black hole in the galaxy's inner regions remains challenging. High-resolution kinematic data help constrain these components, refining models of galaxy structure and evolution. NGC 1277 also challenges our assumptions about the universality of scaling relations such as the M-sigma relation, the tight correlation between black hole mass and the velocity dispersion of stars in the host galaxy's bulge. NGC 1277's black hole is far more massive than what the M-sigma relation predicts for its host galaxy's size and velocity dispersion. This outlier status implies that alternative or additional factors influence black hole growth, perhaps tied to the galaxy's unique formation history or environmental conditions. On the observational front, instruments like the Hubble Space Telescope have been instrumental in resolving NGC 1277's structure and stellar populations, but future facilities promise even greater breakthroughs. The James Webb Space Telescope, with its infrared capabilities, will peer through cosmic dust and probe older stellar populations with enhanced sensitivity. Similarly, upcoming ground-based observatories equipped with adaptive optics will achieve unprecedented spatial resolution, vital for mapping stellar motions near the black hole. Theoretical simulations also play a crucial role in unraveling NGC 1277's mysteries. Cosmological hydrodynamic simulations that incorporate baryonic physics, gas cooling, star formation, feedback processes, are tested against observed properties of relic galaxies. Matching simulations to the detailed data of NGC 1277 helps validate and improve models of galaxy and black hole coevolution, illuminating the pathways by which galaxies can remain compact and quiescent over billions of years. In addition, the study of NGC 1277's supermassive black hole provides valuable context for understanding the early growth of quasars, extremely luminous active galactic nuclei powered by accreting black holes in the young universe. The enormous mass of NGC 1277's black hole suggests that supermassive black holes capable of powering quasars could have formed quickly and early, shaping the reionization epoch and cosmic structure formation. This nexus between local relic galaxies and distant quasars bridges timescales and distances, offering a unified narrative of black hole and galaxy assembly from the dawn of time to the present. The feedback mechanisms observed or inferred in NGC 1277 could be analogues of those that regulated quasar activity in the early universe, highlighting common threads in cosmic evolution. Furthermore, NGC 1277 serves as a laboratory for testing fundamental physics. The extreme gravitational field near its central black hole allows studies of relativistic effects, potentially revealing deviations from general relativity or constraining alternative gravity theories. Monitoring stellar orbits and gas dynamics at such scales requires precision instrumentation and long-term observations, pushing the limits of astronomical technology and methodology. The galaxy also provokes questions about the fate of such relic systems in the future. Will NGC 1277 remain isolated and unchanged? Or could future interactions within the Perseus cluster transform it? Could minor mergers or gas accretion events reignite star formation or alter its structure? Tracking its evolution over cosmic time scales, through observations and simulations, offers a window into the dynamic lives of galaxies in dense environments. In a broader cosmic context, NGC 1277 challenges our perceptions of galactic archetypes. While many galaxies follow well-established evolutionary paths involving growth through mergers and star formation, NGC 1277 exemplifies a different route, one of rapid early assembly followed by prolonged dormancy. Recognizing and studying such diversity is essential for a comprehensive understanding of the universe's tapestry. The implications extend beyond astrophysics. Understanding how black holes grow and regulate galaxies ties into fundamental questions about matter, energy, and the fabric of spacetime itself. Insights from NGC 1277 inform models of cosmic feedback, the distribution of baryonic and dark matter, and the interplay between microphysical processes and large-scale cosmic structure. As research continues, NGC 1277 stands not merely as an astronomical curiosity, but as a crucial piece in the cosmic jigsaw puzzle. Its extraordinary black hole, compact structure, and ancient stars speak of epochs and processes that shape the universe. By probing such objects, humanity edges closer to unraveling the profound mysteries of our cosmos, bridging the gap between the very small and the unimaginably vast. Continuing further, the story of NGC 1277 invites us to reflect on the incredible scales of time and space involved in galaxy evolution and black hole growth. To truly appreciate this, we must imagine the universe as it was over 10 billion years ago, a turbulent, rapidly changing environment filled with dense clouds of primordial gas, nascent stars igniting for the first time, and the seeds of the first galaxies beginning to coalesce under the influence of gravity. NGC 1277's formation likely took place in this early universe, during an epoch called cosmic noon, a time when star formation rates across the cosmos peaked. It is during this era that some galaxies grew quickly by accreting gas and merging with others, forming massive stellar populations. However, while many galaxies continued growing and evolving through mergers, NGC 1277 appears to have rapidly formed the bulk of its stars and then entered a quiescent phase, remaining relatively unchanged ever since. This evolutionary track is unusual and makes it an essential case study for understanding how galaxies can lock in their characteristics early. Astronomers classify NGC 1277 as a relic galaxy, precisely because of this behavior. Such relics provide a fossil record of early galaxy formation, analogous to how ancient trees reveal past climates on Earth. Their compactness and high stellar density imply a rapid and efficient formation, with stars packed tightly into a small volume, unlike many modern galaxies, which are more diffuse and larger due to later mergers and star formation. The key to unlocking the secrets of NGC 1277 lies in understanding the interplay between its stars, dark matter, and the central black hole. The stellar population studies reveal that the galaxy's stars are very old, predominantly formed over 10 billion years ago, with minimal younger populations. This supports the notion that star formation ceased early, likely due to feedback from the central black hole or environmental effects in the Perseus cluster. Regarding the dark matter content, NGC 1277's compactness suggests a high baryon, normal matter, concentration relative to dark matter in its central regions. However, on larger scales, dark matter halos typically envelop galaxies, providing the gravitational scaffolding for their formation. Measuring the extent and shape of NGC 1277's dark matter halo is challenging due to its dense stellar core, but ongoing studies using gravitational lensing and stellar dynamics aim to constrain these properties more precisely. The supermassive black hole at NGC 1277, weighing approximately 17 billion solar masses, is one of the most massive black holes known, especially relative to the size of its host galaxy. This discovery was surprising because it challenges previously established correlations between black hole mass and galaxy bulge properties. The black hole's size is about 14% of the galaxy's total stellar mass, a ratio far exceeding the typical 0.1% observed in most galaxies. This discrepancy prompts astrophysicists to revisit and refine models of black hole and galaxy coevolution. One intriguing implication is that black holes may sometimes grow independently or ahead of their host galaxies, decoupling from the usual feedback processes thought to regulate their joint evolution. Alternatively, NGC 1277's black hole might have grown through an unusual sequence of events, such as mergers with other black holes or periods of intense gas accretion during the galaxy's early life. Understanding how this monster black hole formed and grew so massive in a relatively small galaxy touches on fundamental questions about the mechanisms of black hole feeding and the physical limits of growth. For example, the Eddington limit describes the balance between radiation pressure and gravitational pull that sets an upper bound on how fast a black hole can accrete matter. However, super-Eddington accretion or black hole mergers could enable more rapid growth, possibly explaining NGC 1277's black hole. Observational data from facilities such as the Hubble Space Telescope and integral field spectrographs provide detailed velocity maps of stars orbiting near the galaxy's core. These measurements help astronomers model the mass distribution, revealing the overwhelming gravitational influence of the black hole. Such studies not only confirm the black hole's mass but also provide insights into the dynamics and evolution of the host galaxy. NGC 1277's environment in the Perseus cluster is equally vital for its history. Galaxy clusters are complex environments where interactions, such as tidal forces and ram pressure stripping, can significantly influence member galaxies' evolution. The hot intracluster medium, which emits X-rays, strips gas from galaxies moving through it, potentially quenching star formation. This process may have contributed to NGC 1277's early shutdown of star formation, preserving its relic status. Moreover, the Perseus cluster itself is a massive, dynamic structure, making NGC 1277's survival and relatively undisturbed state a subject of keen interest. Its orbit within the cluster and past interactions could shed light on how galaxies resist or succumb to environmental effects. From a cosmological perspective, studying relic galaxies like NGC 1277 enhances our understanding of galaxy formation pathways and the diversity of evolutionary outcomes. These galaxies serve as benchmarks for testing theories and simulations of galaxy assembly, star formation, and black hole growth across cosmic time. The lessons from NGC 1277 also inform our comprehension of the early universe's most luminous objects, quasars. The extreme mass of its black hole aligns with masses inferred for quasars at high redshift, suggesting that similar rapid black hole growth episodes occurred throughout cosmic history. Furthermore, the study of NGC 1277 advances fundamental physics, enabling tests of gravity in strong field regimes and offering clues about the nature of dark matter and the interplay between baryonic and non-baryonic components in galaxies. As technology advances, next-generation telescopes and instruments will continue to unveil deeper details about this extraordinary galaxy and its colossal black hole, refining our picture of the universe's formative epochs and the forces shaping cosmic structures. Delving even deeper into NGC 1277's characteristics invites exploration of its stellar populations and chemical compositions, which serve as cosmic fingerprints revealing its formation history. Spectroscopic studies have shown that the stars in NGC 1277 are remarkably old, mostly formed over 10 billion years ago, with a high abundance of heavier elements such as iron and magnesium. This indicates that the galaxy underwent a period of intense, rapid star formation early in its life, enriching the interstellar medium with metals from supernova explosions. The abundance patterns suggest a rapid burst of star formation that ceased abruptly, which is consistent with the relic galaxy classification. This early quenching is thought to be influenced by feedback mechanisms, likely from the supermassive black hole itself. As the black hole accreted gas, it would have emitted powerful radiation and jets, heating and expelling the surrounding gas, thus shutting down further star formation. This feedback process is a critical component in current models of galaxy evolution, as it regulates the growth of galaxies and their central black holes. Examining the morphology of NGC 1277 reveals its compact, elliptical shape with a dense core, lacking the spiral arms common to many galaxies. Its size is unusually small compared to typical galaxies harboring black holes of comparable mass, reinforcing the idea that NGC 1277 is a compact relic that escaped the usual evolutionary path dominated by mergers and accretion of gas. In addition to its internal properties, the galaxy's location within the Perseus cluster adds another layer of complexity. The Perseus cluster is one of the most massive galaxy clusters in the nearby universe, filled with hot gas emitting X-rays and containing hundreds of member galaxies. The cluster environment is hostile, with strong gravitational interactions and processes such as ram pressure stripping, which remove gas from galaxies as they move through the intracluster medium. Despite these conditions, NGC 1277 has remained remarkably intact and undisturbed, suggesting a unique orbital path or a protective mechanism that shielded it from disruptive forces. This raises fascinating questions about galaxy survival and the interplay between internal and external forces in shaping galactic evolution. The discovery of NGC 1277's supermassive black hole challenged existing paradigms about the relationship between black holes and their host galaxies. Typically, there is a tight correlation between black hole mass and the bulge mass or velocity dispersion of the host galaxy, known as the m-sigma relation. However, NGC 1277's black hole is disproportionately massive, disrupting this correlation and suggesting that alternative growth pathways or evolutionary histories are possible. One hypothesis is that NGC 1277's black hole formed early and grew rapidly through gas accretion during a short, intense period, before star formation was quenched. Alternatively, it may have grown via mergers with other black holes during galaxy collisions, although the compact nature of NGC 1277 makes this less likely. Studying such exceptions is crucial because they provide insights into the diversity of black hole growth scenarios and help refine theoretical models. It also opens up the possibility that some massive black holes exist in surprisingly small galaxies, which may have implications for searches for intermediate mass black holes and understanding the population statistics of black holes across the universe. From an observational standpoint, measuring the mass of NGC 1277's black hole requires precise data on the motions of stars near the galaxy's center. Instruments like integral field spectrographs enable astronomers to create detailed maps of stellar velocities, allowing the modeling of the gravitational potential and estimation of the black hole's influence. These measurements have been critical in confirming the extraordinary mass of the black hole and understanding its role in galaxy dynamics. Looking forward, advancements in telescope technology, such as the James Webb Space Telescope and future extremely large telescopes, promise to deepen our understanding of galaxies like NGC 1277. These instruments will provide higher resolution observations, enabling more precise measurements of stellar populations, black hole masses, and environmental interactions. Moreover, simulations of galaxy formation incorporating the physics of black hole feedback, gas dynamics, and dark matter distribution are becoming increasingly sophisticated. These models can reproduce relic galaxies under specific conditions, offering theoretical frameworks to interpret observational data. NGC 1277 also holds significance for cosmology, as relic galaxies are snapshots of the universe's early phases. By studying them, scientists gain clues about the conditions and processes during the first few billion years after the Big Bang, shedding light on how the cosmic web of galaxies assembled. NGC 1277 exemplifies the complex and varied pathways of galaxy and black hole evolution. Its massive black hole, compact structure, ancient stellar populations, and cluster environment combine to tell a compelling story of formation, growth, and survival. This galaxy not only challenges existing astrophysical theories but also enriches our understanding of the universe's history, inspiring ongoing research and exploration. It is essential to further investigate the implications of such a colossal black hole residing in a compact relic galaxy, especially when considering the broader context of galaxy evolution and black hole demographics across the cosmos. The presence of a supermassive black hole accounting for roughly 14% of the total stellar mass of NGC 1277 is extraordinary. To put this into perspective, in typical galaxies like the Milky Way, the central black hole mass is only about 0.1% of the bulge mass. This stark contrast raises critical questions. How did NGC 1277's black hole achieve such dominance? And what does this tell us about the coevolution of galaxies and their central black holes? One plausible explanation lies in the galaxy's early evolutionary stages. During the universe's formative years, conditions were highly conducive to rapid black hole growth. Dense concentrations of gas and frequent mergers likely provided ample fuel for the black hole to balloon in mass. However, unlike most galaxies, NGC 1277 appears to have ceased significant star formation and mergers early on, effectively freezing its structure and black hole mass in time. This early quenching halted the typical evolutionary path and preserved the galaxy as a compact, massive black hole host, a relic from an ancient epoch. The discovery of such a system challenges the universality of the M-sigma relation and suggests alternative evolutionary tracks. It prompts astrophysicists to reconsider whether the relationship between black hole and galaxy growth is as straightforward as once thought or if there exist exceptions forged under unique circumstances. Furthermore, the environmental factors play a significant role in shaping galaxies like NGC 1277. Situated within the Perseus cluster, the galaxy's surroundings are dynamic and dense, filled with hot gas and influenced by the gravitational pull of numerous neighboring galaxies. The hostile cluster environment often strips galaxies of their gas, suppressing star formation and encouraging galaxy transformations. Yet, NGC 1277's compact form and high-density stellar core imply it survived these tumultuous processes relatively unscathed. Understanding the dynamics of its orbit and interaction history within the cluster may unlock clues about how some galaxies maintain their integrity amid chaos. In terms of black hole feedback, the energy output from accretion processes in such a massive black hole is staggering. Jets and radiation emitted as matter spirals into the black hole can heat and expel surrounding gas, influencing star formation not just locally but potentially across the host galaxy. In NGC 1277, this feedback likely played a crucial role in halting star formation early, reinforcing its status as a relic galaxy. Moreover, the implications of such black holes extend beyond individual galaxies. Supermassive black holes are key players in the cosmic ecosystem, impacting galaxy clusters, intergalactic gas distribution, and even the reionization era in the early universe. NGC 1277's black hole offers a window into these processes by serving as a living fossil that bridges past and present cosmic epochs. Technological advancements continue to enhance our ability to probe these distant, enigmatic systems. Upcoming telescopes like the Extremely Large Telescope, ELT, and space-based observatories equipped with next-generation instruments will enable astronomers to resolve finer details, detect fainter features, and observe galaxy black hole interactions at unprecedented scales. Additionally, theoretical models and simulations incorporating the complex interplay of dark matter, baryonic matter, and feedback mechanisms are crucial for interpreting observational data. High-resolution cosmological simulations strive to replicate relic galaxies, providing virtual laboratories to test hypotheses about their formation, growth, and survival. In essence, NGC 1277 not only enriches our understanding of black hole galaxy coevolution, but also challenges preconceived notions about the cosmic balance of mass and energy. It highlights the diversity of evolutionary pathways and underscores the importance of relic galaxies as cosmic time capsules, preserving the signatures of an era when the universe was young and dynamic. As research progresses, NGC 1277 will remain a focal point in the quest to unravel the mysteries of galaxy formation and the role of supermassive black holes in sculpting the universe's grand architecture. NGC 1277 stands out in the cosmic landscape not only due to its extraordinary black hole but because it represents a rare and invaluable window into the early universe's galaxy formation processes. Most galaxies we observe today have undergone numerous mergers, starbursts, and evolutionary transformations, but relic galaxies like NGC 1277 have remained largely unchanged since their early formation, making them exceptional cosmic fossils. This means that the galaxy's current properties, its size, stellar population, and black hole mass, carry imprints of conditions that prevailed more than 10 billion years ago, during an era when the universe was in its infancy. Studying these galaxies allows astronomers to piece together the timeline and physical conditions under which supermassive black holes formed and grew at a pace that challenges conventional models. The fact that NGC 1277's black hole comprises a staggering 14% of the galaxy's total stellar mass is an anomaly that compels a re-evaluation of how black holes and galaxies co-evolve. In typical galaxies, there is a relatively tight correlation between black hole mass and the mass of the galaxy's bulge, but NGC 1277 breaks this mold, suggesting that under certain conditions, black holes can outgrow their host galaxies in dramatic fashion. This raises the question of the mechanisms driving such disproportionate growth. During the universe's early stages, galaxies were much more gas-rich and chaotic, with frequent mergers funneling gas into galactic centers, providing fuel for rapid black hole accretion. In NGC 1277's case, it is hypothesized that the galaxy's black hole grew through an early phase of intense gas accretion, potentially aided by massive inflows triggered by gravitational instabilities or mergers with smaller galaxies. However, unlike many galaxies that continue to grow their stellar populations and undergo further mergers, NGC 1277 appears to have entered a quiescent phase relatively quickly. This cessation of star formation is thought to have been caused by feedback from the black hole itself. As the black hole accreted matter, it emitted powerful radiation and jets, which heated and expelled the surrounding gas, effectively shutting down the raw material supply necessary for forming new stars. This feedback loop is a cornerstone of modern astrophysical models, regulating both star formation and black hole growth. But NGC 1277 represents an extreme case where feedback was efficient enough to freeze the galaxy's evolution early on. The compact morphology of NGC 1277 is another intriguing aspect that complements its status as a relic galaxy. Its dense, elliptical structure lacks the extended spiral arms found in many other galaxies, indicative of a formation history dominated by rapid, early star formation and subsequent quenching rather than gradual growth. The stellar population studies reveal that the stars in NGC 1277 are predominantly old, formed in a short, intense burst more than 10 billion years ago. The metallicity of these stars, meaning their content of elements heavier than hydrogen and helium, points to a chemically enriched environment, a signature of multiple generations of supernova explosions that recycled material within the galaxy. Such a rapid enrichment scenario is consistent with a powerful, early starburst phase that ceased once feedback mechanisms took hold. This snapshot of an ancient galaxy preserved in the Perseus cluster offers a direct contrast to more typical galaxies that have more complex and prolonged formation histories. The environment of NGC 1277 adds layers of complexity and interest. Located in the Perseus cluster, one of the most massive and active clusters nearby, the galaxy is surrounded by a hot intracluster medium, a plasma emitting strong X-rays, and a dynamic ecosystem of galaxies interacting gravitationally. Clusters like Perseus are known to subject their member galaxies to harsh processes like ram pressure stripping, where the hot cluster gas strips away cold gas from galaxies as they move through the cluster, effectively starving them of the fuel for new star formation. Despite this, NGC 1277 has remained remarkably intact, with its compact core surviving the rigors of the cluster environment. This resilience suggests that its orbit and position within the cluster may have shielded it from the worst of these stripping processes, or that its early quenching protected it from needing large gas reservoirs. Understanding the trajectory and dynamics of NGC 1277 within Perseus is essential for piecing together how relic galaxies survive in such extreme settings. Astrophysicists employ sophisticated observational techniques to unravel the mysteries of NGC 1277's black hole. Using integral field spectrographs mounted on powerful telescopes, astronomers can map the motions of stars near the galaxy's center with exquisite precision. These velocity maps reveal how the stars orbit the black hole, allowing researchers to model the gravitational influence of the black hole and estimate its mass. In the case of NGC 1277, these measurements confirm the presence of a supermassive black hole weighing in at around 17 billion solar masses, far exceeding expectations based on the galaxy's size. This enormous mass makes the black hole one of the largest ever detected relative to its host galaxy. Such precise measurements rely on high spatial and spectral resolution and represent the cutting edge of observational astrophysics, providing critical data points that challenge existing theories. The extraordinary mass of NGC 1277's black hole also has profound implications for our understanding of black hole formation pathways. It suggests that black holes can grow via rapid, early gas accretion bursts that outpace stellar growth in their host galaxies. Additionally, it raises the possibility that some black holes may have formed from massive, seed, black holes created by direct collapse of primordial gas clouds in the early universe, bypassing the slower growth processes associated with stellar remnants. NGC 1277 thus serves as a key piece in the puzzle of how supermassive black holes reach their colossal sizes within relatively short cosmic timescales. The disruption of the M-sigma relation by NGC 1277 has motivated astronomers to search for other similar galaxies harboring overmassive black holes. Finding more examples would indicate that the co-evolutionary pathways of galaxies and black holes are more diverse than previously thought. It would also provide insight into the frequency and conditions under which black holes can outgrow their hosts, influencing the formation and evolution of large-scale cosmic structures. NGC 1277's existence also touches on the broader theme of galaxy quenching, the processes that halt star formation in galaxies. While many mechanisms can contribute to quenching, including environmental effects, feedback from star formation, and active galactic nuclei, the example of NGC 1277 highlights the potent role of black hole feedback. By injecting energy into the surrounding gas, the black hole prevents cooling and collapse necessary for star formation, effectively shutting down the galaxy's growth. This phenomenon has profound consequences for galaxy demographics and the evolution of the cosmic web. Furthermore, NGC 1277's relic nature provides constraints on the timescales and efficiency of galaxy growth and quenching processes in the early universe. It suggests that some galaxies underwent rapid formation and then experienced early, permanent quenching, surviving in a frozen state to the present day. This insight is vital for understanding the diversity of galaxy evolutionary pathways and refining simulations that seek to replicate the observable universe. From a cosmological perspective, the study of NGC 1277 also informs models of large-scale structure formation. The interplay between black holes, dark matter halos, and baryonic matter shapes the distribution and properties of galaxies across cosmic time. By comparing relic galaxies with more typical systems, astronomers gain clues about how initial conditions and environmental factors drive divergent evolutionary trajectories. In addition to its astrophysical importance, NGC 1277 has captured the imagination of the scientific community and the public alike because it challenges our intuitive understanding of size and mass relationships in the cosmos. The idea that a relatively small galaxy can host a black hole with a mass rivaling the largest known challenges the neat, orderly relationships often assumed in galaxy formation theory. It reveals a universe that is more chaotic, varied, and complex than simplistic models suggest. The technological frontier continues to expand our ability to probe galaxies like NGC 1277 in greater detail. Instruments like the James Webb Space Telescope, with its infrared capabilities, promise to reveal hidden details about the stellar populations and gas content in such galaxies, while next-generation ground-based telescopes will push spatial resolution and sensitivity further. These advances will provide more stringent tests of formation theories and potentially discover new classes of relic galaxies with overmassive black holes. Theoretical astrophysics is also advancing rapidly. High-resolution cosmological simulations now incorporate detailed physics of gas dynamics, star formation, black hole feedback, and dark matter interactions. These simulations can produce relic galaxies under certain conditions, offering virtual laboratories to test scenarios that might lead to galaxies like NGC 1277. By comparing simulation outputs to observational data, researchers refine models and deepen understanding of galaxy black hole coevolution. Moreover, NGC 1277's extreme properties offer a unique laboratory to study the physics of supermassive black holes and their accretion processes. The extreme gravitational environment near such a massive black hole provides insights into relativistic effects, jet formation, and accretion disk physics, all of which are central topics in high-energy astrophysics. Observations across the electromagnetic spectrum, from X-rays to radio waves, help characterize these phenomena. The story of NGC 1277 exemplifies the dynamic and evolving nature of astrophysical knowledge. Each new discovery challenges existing frameworks, prompting revisions, debates, and the development of new theories. It underscores the importance of observational perseverance, technological innovation, and theoretical creativity in uncovering the universe's secrets. NGC 1277 stands as a testament to the complexity of cosmic evolution, inspiring ongoing inquiry into the origins and fate of galaxies and their enigmatic central black holes. The phenomenon of NGC 1277 challenges traditional paradigms of black hole and galaxy coevolution by presenting an extreme outlier that forces astronomers to reconsider the symbiotic relationships governing cosmic growth. Conventionally, supermassive black holes and their host galaxies grow in tandem, with a proportional relationship often expressed through scaling laws such as the m-sigma relation, linking black hole mass to the velocity dispersion of stars in the galactic bulge. NGC 1277 disrupts this pattern, with its black hole mass disproportionately large relative to the galaxy's stellar mass and velocity dispersion. This departure raises fundamental questions about the processes that govern black hole feeding and feedback in the early universe, and whether alternative or additional mechanisms are responsible for the growth of some black holes to extraordinary masses. One potential explanation is the concept of black hole seed mass variation. In the early universe, black holes may have formed from the direct collapse of massive gas clouds, producing seeds with masses ranging from thousands to hundreds of thousands of solar masses, much larger than the typical remnants of the first generation of stars. If NGC 1277's black hole began with such a massive seed, it could have had a substantial head start in growth, rapidly accreting gas and merging with other black holes to reach its current gargantuan size. This hypothesis, while still debated, could explain why some black holes, like the one in NGC 1277, seem overgrown relative to their hosts, as their initial conditions differed drastically from the norm. Accretion physics also plays a crucial role in understanding how the black hole in NGC 1277 achieved its extreme mass. Accretion rates depend on the availability of cold gas, angular momentum, and the efficiency with which material is funneled toward the central black hole. During the early, gas-rich epochs, galaxies could funnel large quantities of matter into their cores via gravitational torques, disk instabilities, or tidal interactions with other galaxies. The accretion process is thought to be self-regulated through feedback. As the black hole accretes, it emits energy that heats or expels surrounding gas, potentially choking off further inflows. In NGC 1277, the black hole may have accreted matter so efficiently that it quickly reached a mass where its feedback became dominant, halting further growth of both the black hole and the galaxy's stellar component. This scenario underscores the delicate balance between feeding and feedback in galaxy evolution. In addition to gas accretion, mergers between black holes during galactic collisions contribute to black hole mass buildup. While NGC 1277 is relatively isolated in terms of recent mergers, its early history may have included multiple coalescences of smaller black holes, combining their masses and accelerating growth. Each merger event would also induce gravitational wave emissions, a prediction now testable with detectors such as LIGO and future space-based observatories like LISA. Detecting gravitational waves from black hole mergers in relic galaxies could provide direct evidence for these growth mechanisms and offer insights into the assembly histories of supermassive black holes. NGC 1277's compact morphology is a hallmark of its relic nature. Unlike more common elliptical galaxies formed through multiple mergers, its stars are densely packed into a small volume, leading to high stellar velocity dispersions that confound simple mass estimates without accounting for the central black hole. This compactness indicates a formation process dominated by early, intense bursts of star formation followed by rapid quenching. The galaxy's stellar population, predominantly composed of old, metal-rich stars, confirms this rapid formation epoch. Spectroscopic studies reveal that these stars formed in a chemically enriched environment, consistent with high rates of supernova explosions recycling metals into subsequent generations of stars. The cessation of star formation in NGC 1277 is attributed largely to the influence of its black hole's energetic feedback. Active galactic nuclei (AGN), powered by accretion onto supermassive black holes, release vast amounts of energy into their surroundings, heating gas and driving outflows that prevent it from cooling and condensing into new stars. In relic galaxies like NGC 1277, this feedback mechanism is particularly efficient, effectively starving the galaxy of star-forming material early in its history. This phenomenon aligns with the concept of AGN quenching, a key process in modern galaxy evolution theories that explains the presence of massive galaxies with little or no ongoing star formation. The environment of NGC 1277 within the Perseus cluster adds additional context to its evolutionary path. Clusters exert strong tidal forces and contain hot intracluster gas that can strip member galaxies of their cold gas reservoirs through ram pressure stripping. This environmental effect, combined with internal feedback mechanisms, further inhibits star formation in cluster galaxies. However, NGC 1277's survival as a compact relic suggests it either avoided severe stripping or had already quenched before entering the cluster environment, preserving its compact stellar core. The dynamics of galaxy orbits within clusters, including infall times and interaction histories, are critical to understanding how galaxies like NGC 1277 remain intact despite the harsh cluster conditions. Observationally, NGC 1277 is a prime target for multi-wavelength studies. Optical and near-infrared spectroscopy provide stellar population ages and metallicities, while X-ray observations probe the hot gas content and AGN activity. Radio observations can detect jets and outflows indicative of ongoing black hole feedback. Combining these data sets yields a comprehensive picture of the galaxy's structure, composition, and energetic processes, shedding light on the complex interplay between black holes and their hosts. The discovery of NGC 1277's overmassive black hole challenged astrophysical assumptions and spurred efforts to identify other galaxies with similar properties. Surveys employing integral field units (IFUs) on large telescopes have begun to reveal a population of compact, high-dispersion galaxies with disproportionately large central black holes. These findings suggest that relic galaxies, while rare, are not unique, and that the early universe may have produced a variety of evolutionary pathways resulting in diverse black hole and galaxy mass ratios. From a theoretical standpoint, modeling the formation of NGC 1277 involves sophisticated numerical simulations that track the gravitational interactions, gas dynamics, star formation, and black hole physics over billions of years. Simulations must reconcile the rapid early growth and quenching of the galaxy with the survival of its compact core through cosmic time. By tuning initial conditions and physical parameters, theorists attempt to reproduce the observed properties of NGC 1277, thereby testing and refining our understanding of galaxy formation and black hole growth. Moreover, the extreme mass of NGC 1277's black hole has implications for gravitational physics and relativistic effects. The environment near such a massive black hole exhibits strong gravitational fields where general relativity governs the behavior of matter and light. Studying phenomena such as relativistic jets, accretion disk emissions, and gravitational lensing in this context provides opportunities to test Einstein's theory under extreme conditions. Observations of stars orbiting close to the black hole could reveal orbital precession and gravitational redshift, further probing the nature of gravity. In the broader cosmological context, NGC 1277's properties inform theories of structure formation and evolution in the universe. The growth of supermassive black holes and their host galaxies is intertwined with the assembly of dark matter halos and the formation of large-scale structures like galaxy clusters and filaments. By understanding the outliers like NGC 1277, cosmologists refine models of how initial density fluctuations in the early universe led to the diverse array of galaxies observed today. The continued study of NGC 1277 also inspires new questions about the fate of relic galaxies and their black holes. As the universe evolves, interactions and mergers may disrupt these ancient systems or feed their black holes further. Observing how relic galaxies fare over cosmic time offers insight into the longevity and stability of such systems, and how black holes influence their surroundings on scales ranging from the galactic core to the cluster environment. Technological advancements promise to revolutionize our knowledge of NGC 1277 and similar galaxies. Future space telescopes equipped with advanced spectrographs and imaging capabilities will enable more precise measurements of stellar populations, kinematics, and black hole properties. Ground-based extremely large telescopes will provide unparalleled spatial resolution to resolve structures at the smallest scales. Additionally, the detection of gravitational waves from black hole mergers will open a new observational window into black hole growth histories. The remarkable story of NGC 1277 exemplifies the evolving nature of astrophysics, where new discoveries continually challenge existing paradigms and expand our cosmic perspective. It highlights the complexity and diversity of galaxy evolution and underscores the critical role of supermassive black holes in shaping the universe's grand tapestry. By studying NGC 1277, we deepen our understanding of how galaxies form, grow, and ultimately mature, revealing the intricate dance between matter, energy, and gravity across billions of years. The concept of galactic relics like NGC 1277 offers a rare glimpse into the conditions of the early universe, preserved in near-pristine form. These relic galaxies serve as cosmic time capsules, offering direct evidence of a formation epoch where star formation was short-lived, yet extremely efficient. Unlike typical galaxies that evolve through countless interactions, gas accretion episodes, and morphological transformations, relics halted these processes early, maintaining their ancient structure and composition. The very existence of NGC 1277 implies that under certain conditions, a galaxy can complete its formative processes within the first billion years of cosmic history and then enter a state of passive evolution, effectively freezing in time. One of the most striking features of NGC 1277 is its velocity dispersion profile. Velocity dispersion reflects how fast stars move within the galaxy and offers clues about the galaxy's total mass and the gravitational influence of its central black hole. In NGC 1277, stars near the center move at extraordinary speeds, a signature indicating the gravitational dominance of the black hole. This steep gradient in stellar velocities not only corroborates the black hole's immense mass but also signifies a tightly bound, compact stellar system, unlike the extended bulges seen in typical elliptical galaxies of similar mass. Additionally, the galaxy's light profile, particularly the steep surface brightness decline toward its edges, suggests a lack of recent mergers or significant dynamical heating. In galaxies that have experienced major mergers, the stellar halo becomes more diffuse and extended due to the mixing of stars from different progenitors. NGC 1277, on the other hand, lacks this extended envelope, reinforcing the conclusion that it has avoided major mergers for over 10 billion years. This observational clue further positions it as a rare relic from a much earlier cosmological era. The black hole's feedback mechanisms, once active, likely played a dominant role in truncating star formation. High-energy jets and radiation expelled by the accreting black hole could have heated the surrounding interstellar medium to the point where it could no longer collapse into stars. This quasar-mode feedback, though brief, may have been potent enough to remove or destabilize star-forming material, effectively sterilizing the galaxy. Once the gas was gone or rendered too hot to cool efficiently, the stellar assembly was locked in, leading to the ancient, red, and dead galaxy observed today. It is also worth exploring the possibility that NGC 1277 represents a previously unrecognized branch of galactic evolution. While the standard evolutionary pathway assumes galaxies grow through mergers and accretion, relics like NGC 1277 hint at an alternative route, rapid formation followed by long-term stasis. This branch may be rare, but it could explain why some black holes appear overly massive. They formed under conditions that favored quick black hole growth without parallel growth in stellar mass. Recognizing this evolutionary fork is crucial to developing a more complete model of galaxy formation. Moreover, NGC 1277 provides a natural laboratory for studying the upper limits of black hole mass in galaxies with minimal confounding variables. In more evolved galaxies, it is difficult to disentangle the effects of mergers, prolonged star formation, and secular processes. In a relic system like NGC 1277, the relationship between the black hole and the galaxy is frozen at an early state, offering a clearer picture of the conditions under which both components initially formed. Studying these pristine systems allows astronomers to refine the calibration of scaling relations used across cosmology and extragalactic astronomy. The surrounding cluster environment also deserves attention. Though NGC 1277 is not the most massive member of the Perseus cluster, it exists in a dynamically rich setting filled with hot gas, dark matter, and frequent interactions. This environment can provide external pressure to retain hot gas around the galaxy while stripping away any remaining cool gas through mechanisms like ram pressure stripping. Such a combination reinforces the quenching that occurred internally, ensuring NGC 1277 remained dormant for billions of years. It also highlights how both internal and external processes can collaborate to shape galactic fate. The implications of NGC 1277 extend into the realm of dark matter studies as well. By analyzing the motions of stars and the gravitational influence required to maintain the galaxy's structure, astronomers can infer the distribution of dark matter. Interestingly, relic galaxies often show a more centrally concentrated dark matter halo, potentially reflecting their early collapse and isolation from later cosmic events that would normally redistribute mass. Thus, NGC 1277 may offer indirect evidence of how dark matter behaves in high-density, early-forming environments. The black hole's potential influence stretches even beyond its host galaxy. Given the mass of the black hole, it could have generated substantial energetic output during its active phase, affecting nearby intergalactic medium. Massive black holes are thought to contribute to heating and enriching the circumgalactic and intergalactic media with metals and energy. The ancient AGN activity of NGC 1277 might have played a part in altering the local environment of the Perseus cluster, contributing to a broader ecological footprint than typically expected from a galaxy of its size. A particularly tantalizing prospect is whether black holes like the one in NGC 1277 could represent intermediate stages between early black hole seeds and the billion solar mass behemoths powering high redshift quasars. Quasars are typically associated with galaxies in the process of rapid growth, yet NGC 1277 seems to have achieved such mass in a relatively short time, and then ceased all luminous activity. If more such galaxies are found, it could imply that rapid black hole growth was not always accompanied by visible quasar activity, thus challenging our understanding of how and when quasars appear. From an observational strategy perspective, NGC 1277 has become a key target in the search for more relic galaxies. Its discovery has inspired astronomers to conduct targeted searches within galaxy clusters and compact galaxy samples, using indicators like high-velocity dispersion, compact morphology, and red color. These observational campaigns aim to build a statistical population of relics to understand how common or rare they truly are. Each additional relic found contributes to a larger narrative about the diversity of galactic life cycles and the conditions under which galaxies can bypass typical evolutionary routes. Advanced instruments like the James Webb Space Telescope, JWST, will play a crucial role in studying galaxies like NGC 1277. With its unprecedented infrared sensitivity and spatial resolution, JWST can peer into the distant past, observing high redshift analogs of present-day relic galaxies. By comparing the properties of early universe compact galaxies with those of modern relics, scientists can trace the continuity of these structures across cosmic time, affirming whether NGC 1277 type systems were once common and gradually faded into the background of galactic archaeology. The continued investigation into NGC 1277's dynamics may also yield insights into the nature of gravitational interactions at small scales. If the central black hole has captured or influenced globular clusters, satellite galaxies, or nearby stellar streams, subtle kinematic signatures could be detected. Mapping these signatures would provide a clearer picture of the black hole's sphere of influence, as well as how it shapes stellar orbits within and beyond the galactic nucleus. Another frontier lies in the simulation of black hole feedback in compact environments. Most cosmological simulations emphasize extended galaxies, where feedback effects disperse energy over a wider area. NGC 1277 presents a more concentrated environment where the energy from the black hole could be even more disruptive. Fine-tuning models to replicate this feedback regime will improve predictions about star formation shutoff thresholds and feedback efficiency as a function of galactic size and density. NGC 1277 remains a cornerstone object in the study of galaxy and black hole evolution. Its stark deviation from expected trends makes it both an anomaly and a key to unlocking deeper truths about the universe's early epochs. Through high-resolution observations, theoretical modeling, and continued comparative studies, this enigmatic galaxy continues to enrich our understanding of cosmic history. One of the most compelling aspects of NGC 1277 lies in the implications it has for early black hole formation scenarios. Theories suggest that shortly after the Big Bang, conditions may have existed that allowed black holes to form directly from massive clouds of gas without first collapsing into stars. These direct collapse black holes could have started out significantly larger than typical stellar mass black holes. In the case of NGC 1277, the black hole may be a descendant of one such ancient monster, formed not in stages, but nearly instantaneously in cosmic terms. This would help explain how it reached over 1 billion solar masses so rapidly while the rest of the galaxy remained relatively modest in size. Considering NGC 1277's potential role as a time capsule, it's also valuable for testing the predictions of hierarchical galaxy formation models. These models assert that small galaxies form first and then merge over time to create larger systems. However, NGC 1277 defies that narrative by appearing to have formed quickly and remained isolated, without participating in the usual hierarchical ladder of growth. It suggests that while the hierarchical model explains much of what we see in galaxy evolution, there are important exceptions that must be understood to complete the cosmic picture. Delving into its stellar population, observations of NGC 1277 reveal a remarkable uniformity in the ages of its stars. Spectroscopic studies show that nearly all its stars are older than 10 billion years, with no significant populations of younger stars. This uniform age distribution is rare and serves as direct evidence that NGC 1277 underwent a rapid and intense burst of star formation early in its history, after which it effectively shut down all further activity. This kind of star formation history is in stark contrast to the more continuous or episodic formation patterns seen in typical galaxies. The compactness of NGC 1277 is another extraordinary feature. Although it is roughly the same stellar mass as the Milky Way, it is only about 1/4 the diameter. This means its stars are packed tightly into a dense spheroidal configuration, with stellar densities approaching those found in the cores of some globular clusters. The result is a galaxy that is small but incredibly massive for its size, earning it the designation of an ultra-compact galaxy. This extreme density likely played a role in the rapid growth of its central black hole by funneling matter toward the nucleus in the early universe. The unusual ratio of black hole mass to stellar mass in NGC 1277 continues to perplex astronomers. While most galaxies have black holes that constitute about 0.1% of the total stellar mass, in NGC 1277, the black hole accounts for nearly 14%. This discrepancy raises fundamental questions about the feedback mechanisms that typically regulate black hole and stellar growth. Did the black hole somehow outcompete the stars for available material? Or did a lack of cold gas prevent star formation while still allowing black hole accretion? These questions remain open and highlight how much there is still to learn about black hole galaxy coevolution. NGC 1277 also invites comparisons with high redshift galaxies, those seen in the very distant universe, when it was only a few billion years old. Many of these early galaxies are compact, massive, and red, much like NGC 1277. By studying NGC 1277 as a local analog to these early systems, astronomers can investigate properties that are difficult to measure at high redshifts, such as stellar orbits, dark matter content, and detailed chemical compositions. In this way, NGC 1277 acts as a bridge connecting our nearby universe to its more distant and mysterious past. Its chemical composition tells another part of the story. NGC 1277 stars exhibit high levels of alpha elements like oxygen, magnesium, and silicon, elements produced predominantly in supernova explosions of massive stars. This chemical signature implies that star formation occurred on very short timescales, less than 1 billion years, before supernova-driven winds swept away the remaining gas. The abundance of alpha elements over iron also supports the idea of rapid chemical enrichment, a hallmark of early universe starbursts. While NGC 1277 is remarkably isolated in terms of its internal evolution, its placement within the Perseus cluster introduces another dimension to its story. Clusters are notoriously hostile environments for galaxies. Ram pressure stripping, tidal interactions, and high-speed flybys often disturb galaxies and transform their morphology. That NGC 1277 has survived relatively untouched in such an environment suggests it may have been on a stable orbit or perhaps entered the cluster after its primary formative phase had already completed. Either way, its survival offers a clue to the environmental conditions that can preserve such relics. The gravitational influence of NGC 1277's black hole extends far beyond its immediate surroundings. If we could observe the orbits of stars deep within the galaxy's center, we would see the black holes pull distorting trajectories and accelerating stellar velocities. These orbits offer a rare opportunity to test general relativity in strong gravitational fields. In particular, observing how light is bent or time is dilated near the black hole can provide real-world laboratories for exploring Einstein's equations and regimes far beyond what we can reproduce on Earth. There is also ongoing debate about whether NGC 1277's black hole mass might have been overestimated. Some models suggest that the high central velocity dispersions could be due to a particularly dense stellar core rather than a supermassive black hole. However, more recent data from high-resolution spectroscopy and improved dynamical models continue to support the presence of an overmassive black hole. If true, it means that the most extreme black holes do not necessarily reside in the most massive galaxies, again challenging conventional wisdom. From a cosmological standpoint, NGC 1277 raises the intriguing possibility that many relic galaxies might exist undetected in the universe. These galaxies are compact, dim in terms of new star formation, and thus easy to miss in surveys that prioritize bright or morphologically distinct targets. Identifying them requires specialized strategies, such as searching for galaxies with extreme velocity dispersions or color profiles indicative of ancient stellar populations. As surveys become more sensitive, especially in the infrared, we may uncover a hidden population of ancient galaxies that have eluded detection until now. Moreover, the black hole in NGC 1277 may hold clues about the upper limit of black hole masses in non-quasar environments. Most black holes exceeding 1 billion solar masses are found in galaxies with active nuclei, visible as quasars or radio galaxies. That NGC 1277's black hole has been dormant for so long suggests a previously underappreciated pathway for creating massive black holes without accompanying luminous activity. This finding could lead to a reassessment of black hole demographics across cosmic history. Studying such galaxies also enhances our understanding of the initial mass function, IMF, which describes the distribution of stellar masses at birth. Some studies of NGC 1277 and similar systems have proposed that their IMFs are bottom-heavy, meaning they formed proportionally more low-mass stars than the Milky Way did. A bottom-heavy IMF would affect everything from the galaxy's total light output to its chemical enrichment and long-term evolution. These implications are vital for interpreting the observable properties of ancient galaxies, both near and far. In the quest to understand galaxy evolution, researchers are increasingly turning to simulations that incorporate hydrodynamics, radiative transfer, and feedback physics. NGC 1277 provides a crucial test case for these models. Can a simulation recreate a galaxy that forms quickly, grows a massive black hole early, and then avoids further interaction for over 10 billion years. If not, what needs to change? Such constraints push the boundaries of our computational models and help refine the physics of galaxy formation. NGC 1277 serves as a humbling reminder of how much remains unknown about the universe. In a field where broad trends and scaling relations are heavily relied upon, exceptions like NGC 1277 challenge complacency and demand a deeper look. It's not just an outlier, it's a beacon, pointing toward parts of the cosmic story that are still hidden in shadow. The eerie stillness of NGC 1277, juxtaposed with the overwhelming mass of its central black hole, continues to perplex astronomers. It's as if we're witnessing a relic from a long-dead civilization, a silent witness to an age when galaxies were forged in ferocious bursts of energy and activity. But unlike its more active contemporaries, NGC 1277 has remained fossilized in form and structure, frozen in time while the cosmos around it continued to evolve, merge, and reshape itself. This stasis makes NGC 1277 a natural laboratory for studying the early universe in exquisite detail, down to the very fabric of its elemental makeup. The morphology of NGC 1277 is notably simple, which in itself is significant. Unlike spiral galaxies with their sprawling arms and dynamic star-forming regions, NGC 1277 is a lenticular galaxy, an intermediate form that possesses a central bulge and a disk but lacks the spiral structure. However, this isn't a disk born of recent activity. It's an ancient formation, long devoid of gas, with stellar orbits shaped more by historical momentum than present-day interaction. This simplicity suggests a lack of recent mergers or accretion events, reinforcing the idea that NGC 1277 has lived an extraordinarily quiet life for billions of years. The surface brightness profile of NGC 1277 also supports its identity as a relic. High-resolution imaging shows that its brightness falls off rapidly with distance from the center, indicating that the bulk of its stars are tightly packed into a relatively small region. This steep gradient in luminosity echoes the structure of high-redshift compact galaxies observed when the universe was young. In those early epochs, galaxies had yet to expand through mergers or the gradual accretion of satellite systems. The fact that NGC 1277 still retains such a profile provides a rare glimpse of that primordial phase, preserved locally. Spectral analyses of the stars in NGC 1277 further enrich our understanding. The light emitted from these ancient stars carries within it a history of their formation. Spectroscopy reveals absorption lines consistent with extremely old, metal-rich populations. This abundance of heavy elements implies that star formation occurred rapidly and efficiently, enriching the interstellar medium before it could be expelled or exhausted. There are few signatures of type I supernovae, which tend to dominate over longer timescales, further emphasizing that the starburst in NGC 1277 was not only intense but also incredibly brief. One might wonder why a galaxy like this never merged with another or experienced the infall of cold gas that could have sparked further star formation. Part of the answer may lie in its location within the Perseus cluster. Galaxy clusters are chaotic environments where high-velocity interactions are common. In such an environment, mergers between galaxies are less likely because their relative speeds are too high for gravitational capture. Instead, galaxies can pass through each other or be stripped of their outer halos, but rarely do they coalesce. This dynamic might have shielded NGC 1277 from merger-driven evolution, allowing it to retain its compact, ancient structure. Furthermore, the galactic environment may have also played a role in quenching star formation early on. The hot intracluster medium that pervades galaxy clusters is filled with high-energy particles and X-ray emitting gas. As NGC 1277 moved through this medium, any cold gas it possessed could have been stripped away, a process known as ram pressure stripping. Without cold gas, new stars cannot form, and the galaxy becomes quiescent. This process might have sealed NGC 1277's fate early in its life, locking in its structure and ensuring its legacy as a cosmic relic. There is also growing interest in the idea that NGC 1277 represents a class of failed giants. In this scenario, The galaxy began life with the potential to become a massive elliptical or spiral but had its development stunted by early black hole feedback. If its black hole formed and grew exceptionally quickly, its immense energy output could have driven out or heated the surrounding gas, halting further star formation and preventing the galaxy from achieving its full size. Such a hypothesis is supported by theoretical models that show how energetic feedback can regulate galactic growth, sometimes to catastrophic effect. The possibility that the black hole grew first and influenced the later evolution of the galaxy turns conventional wisdom on its head. Traditionally, it was thought that galaxies formed first and that central black holes grew afterward by accreting gas and material from their host. But in the case of NGC 1277, the reverse may be true. The black hole may have been an initial seed that consumed vast amounts of gas before stars could form, starving the rest of the galaxy and cementing its small, dense configuration. This chicken or egg scenario is at the heart of many current astrophysical debates. If we accept that NGC 1277's black hole formed first and played a dominant role in shaping the galaxy, then the mechanism of its initial formation becomes critically important. Several theories posit the existence of direct collapse, black holes that formed without going through a stellar phase. Under specific conditions, such as in regions with low angular momentum and strong ultraviolet backgrounds, gas clouds could have collapsed directly into black holes of 100,000 solar masses or more. If such an event occurred at the center of what would become NGC 1277, it could explain its present-day characteristics. Given its unique properties, NGC 1277 has become a focus of multi-wavelength observational campaigns. X-ray observatories, such as Chandra and XMM Newton, have sought to measure the presence of hot gas and potential accretion signatures near the black hole. Meanwhile, radio telescopes like the Very Large Array have searched for signs of past activity that might reveal an ancient AGN, active galactic nucleus, phase. Thus far, the black hole appears dormant, but any past evidence of jets or outflows would further support the notion of early, powerful feedback mechanisms. In terms of kinematics, the stars in NGC 1277 display high-velocity dispersions, especially near the galactic center. This behavior is consistent with the presence of a massive gravitational source, namely, the central black hole. By measuring the motion of these stars and comparing them to theoretical models, astronomers can infer the mass of the central black hole. These dynamical measurements are incredibly challenging, requiring both high spatial resolution and detailed modeling of the stellar distribution, but they are among the most direct ways to weigh a black hole in a distant galaxy. One of the reasons NGC 1277 has become so iconic in astrophysical literature is because it stands as a stark counterexample to many statistical norms. For instance, the well-known M-sigma relation describes a correlation between the mass of a galaxy's central black hole and the velocity dispersion of its stars. Most galaxies fall along this relation, suggesting a coevolutionary path. NGC 1277, however, lies far above it, implying either that its black hole grew independently or that the galaxy's velocity dispersion is being mischaracterized. Either way, its outlier status forces a re-examination of foundational astrophysical principles. The discovery of NGC 1277's black hole also reignited the search for other such systems. Astronomers began reanalyzing archival data, looking for compact galaxies with anomalously high velocity dispersions. Several candidates have emerged, each with their own quirks and mysteries. Some, like MRK 1216 and PGC 70520, show similar relic-like characteristics, suggesting that NGC 1277 may not be alone in its antiquity. If such galaxies are more common than previously thought, then our models of galaxy formation will need significant revision. To fully appreciate the cosmic loneliness of NGC 1277, consider that it may have experienced no major events for over 10 billion years. In a universe that is constantly in flux, where galaxies merge, interact, and evolve, this level of solitude is extraordinary. It would be as if a person lived their entire life in a sealed room while the rest of the world changed outside. NGC 1277 is that cosmic hermit, a reclusive entity that has watched silently from the periphery of the Perseus cluster while the drama of the universe unfolded around it. As we continue to investigate this enigmatic galaxy, new telescopes such as the James Webb Space Telescope and the Extremely Large Telescope may provide deeper insights. Their enhanced sensitivity and resolution could allow for even more precise stellar population studies, uncover the fine structure of the galactic core, and perhaps even detect faint signatures of past activity from the central black hole. Each new observation brings us closer to understanding not just NGC 1277, but the very processes that govern the formation of the first galaxies. The upcoming generation of telescopes promises to revolutionize our understanding of NGC 1277. The James Webb Space Telescope, JWST, with its powerful infrared capabilities, is uniquely suited to probe the older stellar populations of the galaxy. By observing the redshifted light from ancient stars, JWST can provide unprecedented detail about their age, metallicity, and formation history. These parameters are crucial to confirming whether NGC 1277 is truly a relic from the early universe or merely a statistical anomaly that mimics ancient properties by coincidence. Additionally, JWST can search for remnants of gas or dust that might hint at a previously active galactic nucleus phase. Even the faintest traces of warm dust or molecular gas can shed light on the galaxy's dormant past. If such evidence is found, it could validate the theory that NGC 1277 once harbored a powerful quasar-like black hole that blew away its star-forming fuel. Conversely, a complete absence of such material would reinforce the idea that this galaxy shut down before its potential could be realized, a fossilized structure trapped in the infancy of cosmic time. Meanwhile, the Extremely Large Telescope, ELT, with its enormous 39-meter primary mirror, will provide astonishing spatial resolution for ground-based observations. Instruments like Harmony and Mikado will allow astronomers to resolve individual stellar motions within NGC 1277's core. This level of detail could sharpen our estimates of the black hole's mass even further and test whether the stellar velocities truly align with existing models of galactic dynamics, or if we are still missing a critical piece of the puzzle. One intriguing possibility that researchers are beginning to explore is whether NGC 1277 may have once existed in a dramatically different environment. Perhaps it was ejected from a more gas-rich region due to gravitational interactions or galactic collisions. If NGC 1277 was a runaway relic, cast out from a primordial group of galaxies, its lack of subsequent interaction would make sense. Such a scenario would require examining its trajectory and local group environment in finer detail, tracing the motions of nearby galaxies and gas streams to reconstruct its cosmic history. Another line of inquiry involves globular clusters. These dense star clusters orbit galaxies like satellites and can act as fossil records of galactic formation. If NGC 1277 has fewer globular clusters than expected for its mass, it would support the idea of an early shutdown in star formation. Conversely, an unusually rich population of ancient clusters could suggest a brief but incredibly intense period of stellar birth. Studying these clusters, their orbits, metallicity, and distribution, may uncover hidden chapters of NGC 1277's life. Computer simulations are also being refined to model galaxies like NGC 1277. Using cosmological simulations such as Illustris TNG or Eagle, researchers are attempting to recreate conditions under which such a compact and old galaxy could have formed and persisted. These simulations are crucial because they allow us to run virtual universes under different assumptions and watch how various galaxy types evolve, or fail to evolve, across billions of years. Finding digital analogs to NGC 1277 could confirm whether it's a natural, if rare, product of cosmic evolution. What makes this entire investigation more than an academic curiosity is that NGC 1277 challenges the very narrative of galactic development. It suggests that the universe may have produced more ancient, unchanging structures than previously realized. If relic galaxies like this are more common than assumed but simply hard to detect due to their faintness or isolation, we may need to revisit how we count and classify galaxies in the first place. Our maps of the cosmos might be missing vast populations of ghost galaxies that formed early and faded quietly into darkness. This raises philosophical questions as well. In a universe so often characterized by growth, change, and destruction, what does it mean to find something that hasn't changed in over 10 billion years? NGC 1277 isn't just a scientific anomaly, it's a reminder of the cosmic inertia that can freeze certain structures in time. Like a forgotten temple buried beneath cosmic dust, it stands as a testament to what was possible in the dawn of time, and what has since become exceedingly rare. Even more fascinating is how NGC 1277 interacts with the idea of entropy. In thermodynamics, systems move toward disorder, and in cosmology, structures typically evolve toward complexity. More stars, more galaxies, more interactions. Yet NGC 1277 appears to resist that trend. It embodies a form of simplicity, a low-entropy configuration that has somehow remained unperturbed by the chaotic unfolding of the universe. This contradicts expectations and invites speculation about the long-term fate of similar galaxies. From an observational perspective, there is a growing call to search for other galaxies with similar properties. With advances in deep-field surveys, such as those conducted by JWST and future missions like the Roman Space Telescope, astronomers are beginning to target galaxies that are compact, red, and quiescent. If a significant population of these relics is discovered, we may be on the cusp of identifying a whole new category of cosmic fossils, each with its own version of NGC 1277's silent story. Moreover, the study of NGC 1277 has implications for understanding black hole demographics. If such overmassive black holes are more common than thought, then our models for how black holes grow, especially in the early universe, must be revised. Perhaps the seeds of today's supermassive black holes didn't grow gradually over time, but instead formed early, large, and fast, dictating the evolution of their host galaxies from the very beginning. This black hole first paradigm could have profound consequences for our cosmological theories. Another pressing avenue of research involves gravitational waves. If NGC 1277 did once undergo a significant merger in its past, perhaps involving an early black hole coalescence, it might have emitted gravitational waves detectable by future space-based observatories like LISA. Though the event would be ancient, similar systems in the present universe could serve as analogs for such black hole mergers, giving us insight into the kinds of signals we might expect to find. There's also speculation about whether the compactness of NGC 1277 could be harnessed to understand dark matter distribution. Its high stellar density and well-preserved structure make it an ideal candidate for studying how dark matter halos form and evolve in isolation. Precise measurements of its rotation curve, gravitational lensing effects, and stellar kinematics could help constrain the shape and behavior of its dark matter halo, providing clues that go beyond the galaxy itself. There is a haunting beauty in knowing that NGC 1277 exists. Among the billions of galaxies scattered across the cosmos, here lies one that has not aged in the conventional sense. It's not just old, it's timeless. In the symphony of the universe, where most galaxies dance, collide, and burst into bloom, NGC 1277 remains a solemn note of stillness, playing the same quiet tune it began eons ago. And as our telescopes and models improve, so too will our ability to listen more closely to this ancient melody. The potential of NGC 1277 to redefine the cosmic timeline makes it a keystone in the puzzle of galactic evolution. When we peer into its dense and ancient heart, we're not merely observing a distant galaxy, we are witnessing a crystallized remnant of a forgotten era, a preserved chapter from the very beginning of the universe's story. The intensity of the black hole at its core, 10 times more massive than what we would expect for a galaxy of its size, continues to baffle astronomers. How did such a monstrous object form so early? What conditions led to this extreme divergence from the galactic norms we observe in the modern universe? These questions continue to circulate across research institutions and observatories, fueling debates and driving the next generation of astronomical investigations. There is a growing recognition among astrophysicists that the standard models of galaxy formation may not be broad enough to account for the existence of relics like NGC 1277. Current models assume a relatively smooth transition from early starburst phases to modern spiral or elliptical structures through repeated mergers and accretions. Yet NGC 1277 sits outside this timeline. It appears to have skipped the gradual growth stages that define typical galactic life cycles, instead forming nearly all its mass rapidly and then locking into a static state. This deviation demands either a modification of the standard cosmological frameworks, or the addition of a new category of galactic evolution scenarios, those of rapid formation and early dormancy. This could also shed light on the mysterious epoch known as Cosmic Dawn, a period when the first galaxies began to light up the universe with starlight. NGC 1277 may be a rare survivor from this age, a structure that formed under extreme pressures and temperatures shortly after the Big Bang, then cooled quickly and remained insulated from the violence of galactic evolution. Understanding its chemical composition, especially the prevalence of heavy elements in its stars, could offer insight into the nucleosynthesis processes of the early universe, when the first elements beyond hydrogen and helium were forged in the hearts of stars. Its location in the Perseus cluster also adds another layer of intrigue. Surrounded by some of the largest and most active galaxies in the nearby universe, NGC 1277 remains undisturbed, a silent sentinel in a realm of giants. This stark contrast raises questions about environmental influence. Why has it remained so untouched in such a chaotic neighborhood? Did it form early and sink toward the cluster center through dynamical friction? Or has it somehow managed to maintain a low enough profile to avoid the gravitational attention of its massive neighbors? The gravitational dynamics of the Perseus cluster could provide clues. Advanced simulations and X-ray observations suggest that galaxy clusters exert enormous tidal forces that can strip smaller galaxies of gas and stars. However, NGC 1277 retains a significant stellar mass and shows no signs of having been stripped or disrupted. This indicates an exceptional internal coherence, possibly a result of its extreme compactness and dense stellar population. These features may provide a protective shield, preserving its core and allowing it to resist the cluster's gravitational turbulence. Another theory gaining traction is that NGC 1277 may be a failed brightest cluster galaxy, BCG, a galaxy that had the potential to dominate the cluster but was halted in its development. If true, this would offer a fascinating perspective on galactic evolution. Not all early formed galaxies fulfilled their potential. Some may have been cut short due to environmental or internal mechanisms, leading to a diversity of galactic fates from the same starting point. This galactic failure model introduces a new dimension to how we evaluate and compare galaxies. Furthermore, the debate over its classification continues. Some argue that it fits better into the category of ultra-compact massive galaxies, UCMGs, which are believed to be relics from the early universe that never underwent significant merging. Others maintain that its characteristics are so extreme that it warrants a new classification altogether, perhaps hypercompact relic galaxies. These debates are not just semantic. They influence how observational campaigns are structured and how databases are curated. If NGC 1277 represents a new class, then a global effort to find its cousins must begin in earnest. High-resolution spectroscopy will be instrumental in this pursuit. By analyzing the absorption lines in its spectrum, astronomers can determine the velocities and chemical compositions of its stars, thereby reconstructing its star formation history in unprecedented detail. So far, the evidence suggests that over 90% of its stars formed in a single burst over 10 billion years ago, with no significant activity since. This makes it one of the oldest and most passive galaxies ever observed, qualities that align with the relic theory. The implications stretch beyond NGC 1277 itself. If such relic galaxies are more common than currently recognized, they could serve as crucial benchmarks for testing theories about the initial mass function, IMF, of stars, the behavior of dark matter in early galaxies, and the growth of black holes in dense environments. They could also help clarify the role of feedback processes, especially those driven by supermassive black holes that shut down star formation and stabilize galaxies. In the broader context of cosmic archaeology, NGC 1277 is akin to discovering a perfectly preserved fossil in the middle of a bustling metropolis. It's a temporal anomaly that offers a glimpse into a world long vanished. It invites us to reconsider our assumptions about what a galaxy is, how it forms, and what it can become. It challenges the deterministic view of galactic evolution and reminds us that, sometimes, cosmic destiny is dictated by a single epoch of extraordinary conditions followed by eons of quietude. As we continue to refine our instruments and extend our reach deeper into the universe, it's likely that more galaxies like NGC 1277 will be uncovered. Some may be more massive, others more isolated, and still others more heavily influenced by black hole feedback. Each will tell a slightly different story, but all will contribute to a new understanding of how galaxies can evolve, or cease evolving, under extreme cosmic conditions. The legacy of NGC 1277 may ultimately be its role as a scientific provocateur. It defies convention, demands explanation, and opens new paths of inquiry into the dark, early corners of the cosmos. It teaches us that the universe is not a homogeneous place where all galaxies follow the same script. Some, like NGC 1277, write their story in a single act, and then remain still, waiting for curious minds across the cosmos to rediscover them. Its silence is not emptiness, but endurance. NGC 1277 stands as a galactic relic from the dawn of time, holding within its ancient stellar populations a story that predates even the Milky Way. Its mere existence implies the universe was once a place of exceptional variety, a cosmic wilderness where not every galaxy followed the same evolutionary trail. This diversity in galactic behavior opens a new chapter in our understanding of cosmic history, one in which outliers like NGC 1277 are not just anomalies, but keystones to the broader puzzle of universal formation. When we peer into this enigmatic structure, we are essentially gazing into a time capsule from the primordial universe. Unlike many galaxies that continually evolve through the acquisition of new material and interactions with neighboring systems, NGC 1277 is static, its shape and mass seemingly frozen in time. This resistance to change is extraordinary. It means that the galaxy has managed to exist in a largely undisturbed state for over 10 billion years, preserving characteristics that have long vanished in other galactic systems. At the heart of this silent relic lies an overgrown monster, a supermassive black hole whose mass is estimated at 17 billion solar masses, comprising a significant portion of the galaxy's entire mass. This black hole is not just large, it is disproportionately massive relative to the galaxy that houses it. In most galaxies, the central black hole makes up a tiny fraction, often less than 1%, of the galaxy's stellar mass. But in NGC 1277, this black hole constitutes nearly 14% of the total mass, turning conventional wisdom on its head. This has fueled debates about whether NGC 1277 formed around the black hole, or if the black hole grew so quickly and intensely in the early universe that it stunted the galaxy's further development. The extraordinary size of the black hole may also be responsible for the galaxy's inactivity. Its powerful gravitational influence and energetic feedback would have disrupted star-forming clouds and expelled gas that could otherwise fuel further star formation. In this way, the black hole not only sits at the center of the galaxy physically but also figuratively as the primary architect of its destiny. It may have consumed more than just matter, it may have consumed the future of its host. Analyzing NGC 1277 also provides a rare opportunity to test and challenge the M-sigma relation, which links the mass of a galaxy's central black hole to the velocity dispersion of its stars. This empirical relation has served as a cornerstone for models of galaxy formation and black hole coevolution. However, NGC 1277 is an outlier to this rule. Its black hole is far too massive for the stellar velocities observed, suggesting that either the relation breaks down in some galaxies or that the early universe allowed for more chaotic and unpredictable black hole growth than previously believed. The compactness of the galaxy is another unique trait. While most modern galaxies have extended halos of stars and gas, NGC 1277 is unusually tight and dense. Its stars are packed into a spheroidal distribution that measures just a few kiloparsecs across. This dense configuration not only helps preserve the galaxy's structure over billions of years, but also makes it an ideal laboratory for studying the physics of high-density stellar systems. Scientists can use NGC 1277 to explore gravitational interactions under extreme conditions, where every star is influenced by the collective mass of millions of others. Beyond its physical traits, the chemistry of NGC 1277 stars offers more evidence of its ancient origin. Spectral studies show a population of old, metal-rich stars with very little sign of recent star formation. This means that the stars in NGC 1277 were forged in a single, intense burst of activity over 10 billion years ago, and have remained largely unchanged since. The lack of metal-poor stars also suggests that the galaxy underwent rapid chemical enrichment early in its life, likely driven by a first generation of massive, short-lived stars that exploded as supernovae and seeded the galaxy with heavier elements. This early enrichment and the absence of subsequent star formation are signs of what astronomers call galactic quenching, the process by which a galaxy abruptly halts all new star formation. In the case of NGC 1277, the quenching was likely caused by the energetic outbursts of its central black hole, which may have heated or expelled all the cold gas required to form new stars. Once this gas was gone, the galaxy had no fuel left, effectively locking its structure and composition into place for the remainder of cosmic history. The surrounding environment of NGC 1277, namely the Perseus cluster, provides a stark contrast to its stillness. The cluster is a dynamic ecosystem of interacting galaxies, dark matter, and superheated gas. And yet, amid this chaotic milieu, NGC 1277 remains undisturbed. This suggests a history of isolation despite its crowded locale. It's as if NGC 1277 fell into the Perseus cluster long after it had finished evolving, surviving the infall without major disruption thanks to its compact structure and possibly a trajectory that kept it away from other galaxies' disruptive gravitational fields. The dark matter content of NGC 1277 also remains a point of contention. Studies suggest it may have far less dark matter than expected, raising questions about how it formed and remained intact. In most galaxies, dark matter acts like cosmic scaffolding, holding the visible matter together and protecting it from being stripped during interactions. The lack of such scaffolding in NGC 1277 challenges the conventional narrative that dark matter is essential for galactic longevity. Could this mean that in the early universe, some galaxies formed differently, perhaps collapsing directly from primordial gas without requiring extensive dark matter halos? This line of inquiry naturally leads to broader cosmological implications. If NGC 1277 and others like it represent an alternative path of galaxy formation, it could mean our current models are incomplete or biased by the types of galaxies we typically observe. Most of our data comes from galaxies that are bright, active, and large. But what if these quiet relics, hiding in the shadows of the universe, are more common than we think? We may be overlooking an entire population of ancient, compact, black hole-dominated galaxies that never evolved beyond their initial formation. To find more galaxies like NGC 1277, astronomers are now employing a range of techniques, from gravitational lensing to deep-field surveys using infrared and radio telescopes. The James Webb Space Telescope, with its unparalleled ability to peer into the early universe, is poised to play a central role in this search. Already, preliminary data from its deep-field images hint at the existence of ultra-compact, high-redshift galaxies that share some traits with NGC 1277, suggesting that these relics may have been more common in the early universe than previously believed. As more of these objects are discovered, a new picture of galactic diversity is beginning to emerge. It is a picture where galaxies are not monolithic entities marching along a single path of evolution, but rather a menagerie of structures shaped by different initial conditions, environments, and internal processes. NGC 1277 is the tip of this hidden iceberg, an ancient artifact pointing the way toward a deeper understanding of how the cosmos assembled its vast structures. NGC 1277's eerie preservation through cosmic time becomes even more remarkable when considering the turbulent environments in which galaxies usually find themselves. Galactic clusters are arenas of constant motion, interactions, mergers, and sometimes outright collisions. They are battlegrounds where galaxies are ripped apart by gravitational forces, stripped of gas by intra-cluster media, and reshaped by the influence of their neighbors. Yet in the middle of this cosmic coliseum, NGC 1277 stands, unscathed, seemingly defiant of the chaos around it. The galaxy's ability to avoid major mergers or disruptions for over 10 billion years speaks to a delicate balance of factors: its initial conditions, its internal structure, and its orbital dynamics within the cluster, all aligning in a rare, near improbable configuration. This raises important questions about the nature of galactic fate. While we often consider galaxies to be dynamic, fluid systems constantly evolving through accretion and interaction, NGC 1277 suggests that there are exceptions, instances where evolution halts and structure remains suspended in time. If galaxies like NGC 1277 are relics, their discovery is akin to finding a perfectly preserved ancient city, untouched by centuries of war, weather, or modernization. The lessons they hold could be foundational, offering a glimpse into what galaxies might have looked like in the universe's earliest chapters, before the grand cosmic ballet of interaction and transformation took center stage. Studying the dynamics of NGC 1277 is another vital piece of the puzzle. Observations show that the stars within the galaxy move at extremely high velocities, not dissimilar to the speeds seen in elliptical galaxies much larger in size. This high-velocity dispersion is one of the key indicators of the gravitational grip exerted by its central black hole. In a typical galaxy, such rapid stellar motion would be accompanied by a correspondingly high mass in the surrounding galaxy, often in the form of extended stellar or dark matter halos. But in NGC 1277, much of that mass seems to be concentrated in its central region. The implications are profound. It is as if the entire galaxy was built around a gravity well so powerful that it bent not only light and matter but also the evolutionary trajectory of its host. Another mystery involves the way NGC 1277 emits light. Its spectral energy distribution lacks the signatures of young, hot stars: no ultraviolet glow, no emission lines from ionized gas, no infrared indicators of dusty star-forming regions. Its light is old, red, and tired, streaming from ancient stars that have been burning steadily for billions of years. There is a haunting beauty to such an object, a galaxy that blazes not with the youthful energy of creation but with the quiet glow of age and endurance. It is a beacon from the ancient universe, whispering secrets through its light, begging us to understand how it came to be and why it still exists in such a pristine state. What role, then, did the cosmic web, the vast structure of filaments, voids, and nodes that make up the universe's large-scale architecture, play in the formation of NGC 1277? Some theories suggest that this galaxy may have originated in a low-density environment, away from the bustling highways of matter that fuel the growth of most galaxies. It may have formed early and quickly, collapsing into its compact state before the large-scale flows of gas and dark matter could feed it further material. If true, this would help explain why NGC 1277 has remained so isolated in terms of its development, despite now residing in a busy cluster. It wasn't that it avoided evolution by chance; it may have evolved differently from the very beginning. Its location in the Perseus cluster also opens up fascinating questions about galactic migration. Did NGC 1277 form within the cluster itself, or was it captured later, drawn in from a more remote, tranquil region of space? If the latter is true, then this galaxy has made a perilous journey across cosmic distances and survived the gauntlet of gravitational tides and high-speed encounters that typically transform galaxies into new shapes. Understanding this journey could offer critical insight into how structure and motion affect galactic survival, and how some galaxies preserve their original identities even when embedded in hostile environments. Another area of interest lies in the elemental abundances within NGC 1277. Initial studies indicate high metallicity, especially among its older stars. This suggests a history of rapid, intense star formation early on, followed by a sharp and permanent cutoff. This pattern is consistent with what astronomers call a monolithic collapse model of galaxy formation, where a galaxy forms quickly and violently from a single, large cloud of gas and then stabilizes without much external influence. This stands in contrast to the more commonly accepted hierarchical model, where galaxies grow through the slow accumulation of smaller structures over time. NGC 1277 might be a real-life relic of the monolithic age, a survivor of a cosmic era long gone. The search for analogues to NGC 1277 is ongoing, and it remains a rare object in the observational record. However, other galaxies, such as NGC 1271 and NGC 1600, have shown traits that suggest they too may host overgrown black holes or have unusual formation histories. These galaxies are being scrutinized with powerful instruments like the Hubble Space Telescope, ALMA, and JWST. Each new discovery adds to a growing sense that the early universe may have produced more exotic, high-density, black hole-driven systems than previously thought. If this is the case, the traditional evolutionary pathways laid out in our cosmological models may need significant revision. There is also an emerging line of theoretical research that explores how feedback from supermassive black holes could fundamentally alter galaxy formation. In this framework, a sufficiently active black hole early in a galaxy's life could produce winds and radiation so intense that it either drives gas out of the galaxy entirely or heats it to the point where it can no longer cool and collapse into new stars. This feedback loop could permanently quench star formation and preserve the galaxy's compact form. NGC 1277 may represent the ultimate expression of this process, a galaxy whose evolution was not just influenced but completely dominated by its central black hole. From a technological standpoint, observing NGC 1277 poses significant challenges. Its distance from Earth means that even with our most advanced telescopes, we are seeing the galaxy as it existed billions of years ago. Its compactness also means that its light is concentrated, making it harder to tease out individual features or structural details. But thanks to advances in adaptive optics and spectroscopy, astronomers have been able to map its internal motions and stellar populations with increasing precision. Every pixel of data from this galaxy is scrutinized for clues, like an archaeological site where even the dust matters. On a philosophical level, NGC 1277 invites us to reconsider what it means for something to be alive, or dead, in a cosmic sense. Though the galaxy is no longer forming stars, and its structure is largely inert, it continues to exert influence through its immense gravity and luminous memory. It exists not as a corpse but as a monument, a preserved witness to a universe that was once more violent, more chaotic, and more diverse than the one we know today. Its existence forces us to appreciate that even in the realm of galaxies, where lifespans stretch across eons, some stories end early and remain frozen in time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.